Settle in, dear dreamer, as we drift through the cosmos at the speed of thought. Let your breathing slow to match the ancient rhythm of the universe itself, where time moves like honey through amber and distance becomes just another word for wonder. Welcome back to the Sleepy Professor, where curiosity meets tranquility in the gentle embrace of the cosmos. I'm delighted you found your way here tonight. Whether you're nestled beneath soft covers that hold the warmth of 1,000 sleeping nights, curled into a favorite chair that knows the exact shape of your contemplative moments, or simply letting your mind wander while the world grows quiet around you, that magical hour when streetlights become stars and silence becomes a language all its own. Tonight we'll be drifting through the universe's most serene and silent places, realms so cold that time itself seems to hold its breath, waiting. These are corners of existence where atoms barely whisper their quantum secrets, where heat becomes a distant memory like summer recalled in deepest winter, and where the very fabric of reality reveals its most elegant secrets in crystalline perfection. So let your breathing slow to match the pulse of distant pulsars. Allow your thoughts to settle like stardust on the velvet of space, and join me on this gentle voyage to the frozen poetry of deep space. The universe, you see, is mostly a cold place. Not the bitter cold of a February morning that makes you pull your coat tighter, but a profound ancient cold that speaks of vast distances and the patient mathematics of entropy. It's a cold that holds stories, the biography of every photon that has travelled from the birth of galaxies to reach your drowsy eyes, the memoir of matter itself as it learns to dance more slowly, more gracefully, approaching the ultimate stillness that lies at the heart of all things. Before we begin our cosmic lullaby, I'd love to hear from you in the comments below, like whispered confidences shared in the darkness. Where are you listening from tonight? Perhaps it's the soft glow of evening wherever you are, when the day's harsh edges blur into something kinder. Or maybe you're stealing a few peaceful moments during a quiet afternoon, when sunlight slants through windows and carries dust motes like tiny planets in their own gravitational ballet. Your presence here, from whatever corner of our spinning world, adds warmth to this shared journey through the cold, a reminder that consciousness can kindle its own fire, even in the vast refrigerator of space. If this gentle exploration helps ease your mind or sparks that wonderful drowsy curiosity, the delicious state where wonder and sleepiness dance together, a like and subscription would mean the world to me. It keeps these midnight voyages alive, sustaining this little corner of the internet where science becomes lullaby, where equations dissolve into dreams, and who knows, you might find yourself drifting off somewhere between the rings of Saturn and the whispered songs of distant nebula, your dreams flavored with the taste of liquid nitrogen and the mathematics of absolute zero. Now, a gentle warning, delivered with the tenderness of a parent checking on a sleeping child. I try to craft these journeys to be just interesting enough to occupy your wandering mind, but not so captivating that they chase away sleep like bright lights scattering shadows. But if you do find yourself wide awake at the end, at least you'll greet tomorrow knowing more about quantum physics and cosmic temperatures than most earthbound souls ever will. You'll carry with you the secret knowledge that the universe is far stranger and more beautiful than our daily lives suggest, that behind the ordinary world of thermostats and winter coats lies a reality where matter can forget how to behave normally, where physics becomes poetry, and where the coldest places in existence teach us the most profound lessons about heat, motion, and the meaning of absolute stillness. So adjust your pillow like an astronaut preparing for a journey to distant stars. Let your eyelids grow heavy if they wish, heavy with the accumulated starlight of billions of years, heavy with the gravitational pull of dreams, and let's begin our slow drift toward the frozen edges of everything. These are places where warmth is but a memory preserved in amber, where time moves like honey through the crystalline structure of space itself, and where atoms barely dare to dance, moving with the reverence of monks in meditation. Please remember, As we embark on this journey through temperatures so extreme they border on the mystical, this voyage is for wonder and rest, not medical advice. I'm simply a sleepy professor, sharing the universe's quieter stories, tales told in wavelengths too long for ears to hear, in temperatures too cold for skin to feel, in distances too vast for minds accustomed to earthly scales to fully grasp. But that's precisely why they make such perfect bedtime stories. They carry us beyond the familiar into realms where imagination and physics merge into something approaching magic. The cold we'll encounter tonight isn't empty or hostile. It's pregnant with possibility, rich with the potential energy of stillness. It's the universe's way of holding its breath, creating spaces of such profound quiet that the smallest quantum fluctuations become symphonies, where virtual particles pop into existence just to experience the luxury of absolute zero before dissolving back into the foam of space-time itself. The gentle nature of cold when physics becomes philosophy. Let's begin with something beautifully simple yet profound, like watching a single snowflake land on your palm. What exactly is this thing we call cold? It's a question that seems childish until you realize it contains the seeds of some of physics' deepest insights. You know cold intimately, of course. It lives in your body's memory, the sharp bite of winter air against your cheek that makes you gasp involuntarily, the shock of bare feet on a tile floor at midnight when you've forgotten the world exists beyond dreams, the way your breath becomes visible, clouds on a January morning, transforming the invisible atmosphere into art with each exhalation. Your body speaks fluent cold in a language older than words. Every nerve ending, every shiver, every instinctive reach for warmth tells the story of your ancestors' long negotiation with a universe that tends toward freezing. But here's where science becomes poetry, where the prosaic transforms into something approaching mystical. Cold isn't really a thing at all, it's the absence of something else. Heat, and heat in turn, is simply movement, not the grand, visible movement of planets orbiting stars or galaxies, rotating through space-time, but the secret, invisible movement that happens at the scale of atoms, a microscopic choreography so fundamental that everything you've ever touched, every surface that has supported you, every breath of air that has sustained you, participates in this eternal dance. Every object around you, no matter how perfectly still it appears to your drowsy eyes, is actually alive with microscopic motion so vigorous it would exhaust you to watch. The atoms in your pillow, those cotton fibers that cradle your dreams, are vibrating with an energy that never rests. The molecules in the air you breathe are careening around your room at speeds that would make a race car driver dizzy. Even the seemingly solid walls that contain your private universe are dancing internally with the enthusiasm that never dims, atomic celebration that has been going on since the moment those materials first condensed from stellar nurseries billions of years ago. Picture this, and let the image settle into your mind like sediment in still water. If you could shrink down small enough to watch the molecules in a warm cup of tea, perhaps chamomile, perhaps something stronger, you'd witness a magnificent chaos that puts any human dance floor to shame. Millions upon millions of tiny dancers, each no bigger than a few atoms linked together, colliding and spinning and vibrating with such infectious enthusiasm that their collective motion creates what we feel as warmth against our palms, what we taste as liquid comfort on our tongues. The more frenzied their dance, the hotter things become, like a nightclub where the music keeps getting louder and the dancing more ecstatic. The gentler their movement, the cooler we perceive them to be, like that same nightclub in the early morning hours when the music fades and couples sway together in peaceful exhaustion. Temperature, you see, is just our macroscopic name for this microscopic partying. Cold, then, is like slowly turning down the music at this molecular party. As the dance grows calmer, as the jostling settles into a more peaceful rhythm like couples finding their comfortable sway, temperature drops. The atoms begin to move with less violence, less chaos, more grace. They stop colliding with the enthusiasm of teenagers and start moving with the measured dignity of grandparents dancing to music only they can hear. And if we could somehow convince every single atom to sit perfectly still, which, spoiler alert, that we'll explore more deeply as our journey continues, we can't. We'd reach a place called absolute zero. It's a destination that exists more in theory than in practice, like a mathematical heaven that can be approached but never quite reached. But that's a tale for deeper into our journey, when we've learned to breathe with the rhythm of quantum mechanics and dream with the logic of thermodynamics. For now, simply imagine coldness as the universe's way of whispering instead of shouting, of walking instead of running, of settling into stillness like a cat finding the perfect sunny spot for a nap, that kind of settling that takes account of every ray of light, every warm surface, every perfect alignment of comfort and physics. The languages of temperature. How humans learn to count the dance. We humans, in our endless need to quantify and categorize the universe, have invented several ways to measure this cosmic dance of motion. It's rather touching, really. Here we are, biological creatures, adapted for a narrow range of thermal conditions, trying to create scales that encompass everything from the heart of stars to the void between galaxies. Most of us know Celsius, invented by Swedish astronomer Anders Celsius in 1742, where water freezes at a tidy 0 degrees and boils at 100, numbers that feel logical and clean, like the universe cooperating with our decimal preferences. There's something deeply satisfying about this scale, the way it makes water's phase transitions into round numbers, as if nature were trying to make chemistry homework easier. Then there's Fahrenheit, used primarily in the United States with the stubborn affection Americans reserve for their unique measurements, where water's freezing point sits at 32 degrees and boiling happens at 212. These seemingly random numbers come from the creative mind of 18th century physicist Daniel Fahrenheit, who based his scale on a mixture of water, ice, and ammonium chloride for his 0 point and human body temperature for his upper reference. Charmingly arbitrary, really like measuring the universe with your grandfather's favorite walking stick. But for scientists, and for our journey tonight through temperatures so extreme they challenge imagination, there's a more elegant scale called Kelvin, named after Lord Kelvin, a man who understood that temperature deserved a scale as absolute as the phenomenon it measured. This scale begins not at some arbitrary freezing point chosen for human convenience, but at the very bottom of the temperature spectrum, absolute zero. 0 Kelvin equals minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit, the theoretical point where all atomic motion would cease completely, where the universe's eternal dance would finally stop to catch its breath. What makes Kelvin beautiful in its scientific honesty is that it starts where physics says temperature really begins, or rather ends. Since temperature is really just a measure of how much kinetic energy particles possess, how much they jiggle and vibrate and careen around their microscopic neighborhoods, why not start at 0 energy and count upward? No negative numbers to confuse the mathematics, no arbitrary reference points based on the convenience of human experience, just a clean measure of cosmic motion from perfect stillness to stellar fury. On the Kelvin scale, room temperature becomes 293.15 K, and suddenly our comfortable world seems like a rather energetic place. Your body temperature of 37 degrees Celsius transforms into 310.15 K, revealing that you're actually a pretty vigorous collection of dancing atoms, maintaining their choreography with remarkable precision. The surface of the Sun, at about 5,778 K, seems both incredibly hot and somehow more comprehensible when placed on this absolute scale. How we feel the cold, the intimate physics of thermal sensation. But let's drift back from the abstract mathematics and consider something more intimate, more immediately real: how your body experiences cold. This isn't simply about the raw temperature measured by some digital thermometer, but about the complex thermal negotiation happening between your warm living flesh and the cooler world around you. The sensation isn't just about the numbers on a scale, it's about how quickly your precious body heat is being drawn away, like warmth flowing downhill into the vast cold reservoir of the universe. Your skin doesn't have tiny thermometers embedded in it reading out precise temperatures. Instead, it has thermal sensors that detect the rate of heat flow, the speed at which your internal fire is being pulled into the surrounding coolness. Step outside on a winter morning wearing just a t-shirt, and you'll feel cold, not because the air is aggressively attacking you with frigid energy like some meteorological predator, but because your body's precious warmth, that 98.6 degrees Fahrenheit, that represents the sum total of millions of years of evolutionary fine-tuning, is rushing away, drawn into the cooler air like water flowing downhill, following the inexorable laws of thermodynamics that govern everything from cooling coffee to dying stars. This is why a damp 5 degrees Celsius morning might feel more bone-chilling than a dry -10 degrees Celsius evening, even though the thermometer would suggest otherwise. Moist air is better at conducting heat away from your skin. Water molecules are particularly good at carrying thermal energy, like tiny thermal pickup trucks hauling your warmth away. The dampness creates better thermal contact between your skin and the cold air, accelerating heat loss and making you feel colder faster than the raw temperature alone would predict. Wind does something similar, which is why meteorologists speak of wind chill. It's not just poetry or marketing for winter weather, but actual physics. Moving air strips away the thin boundary layer of warmed air that normally clings to your skin like an invisible thermal blanket. This layer, just a few millimeters thick, represents your body's attempt to create a personal microclimate. Wind disrupts this delicate thermal architecture, forcing your body to constantly rewarm fresh air instead of basking in its own thermal exhaust. Interestingly, our perception of cold varies wildly from person to person in ways that reveal the beautiful subjectivity of physics. Some souls seem immune to winter's bite, walking around in shorts during snowstorms like they're carrying some internal fusion reactor, while others reach for sweaters the moment autumn's first leaf falls, as if they're thermally connected to some cosmic freezer. Our skin contains specialized nerve endings called thermoreceptors that alert us to temperature changes, but they're evolved more for survival than precision measurement. These sensors care more about keeping you alive than about accurate temperature readings. They're the biological equivalent of smoke alarms, better at preventing disaster than providing precise information. Your fingertips might scream warnings about impending frostbite, while your core temperature remains perfectly comfortable and stable. This makes evolutionary sense. Fingers and toes are expendable in a survival situation, but maintaining core temperature is literally a matter of life and death. Your body's thermal management system has priorities, and it will sacrifice your extremities to keep your vital organs warm, like a building's heating system that shuts off heat to empty rooms to keep the important areas comfortable. In the most extreme cases, cold can actually burn, creating a sensation nearly identical to heat damage, proof that extremes, even opposite ones, often lead to similar biological destinations. If you've ever touched dry ice, frozen carbon dioxide at -78.5 degrees Celsius, or had the misfortune of skin meeting metal in sub-zero weather, you know this peculiar sting. At extremely low temperatures, the cold causes water in your skin cells to freeze and expand, rupturing cell walls in damage that looks remarkably similar to heat burns. Your nervous system, faced with cellular damage it wasn't designed to categorize, simply reports injury in the same way it would report thermal burns from touching a hot stove. Cold as friend, not foe. The unlikely alliance. We tend to think of cold as an adversary, something to battle with blankets and hot chocolate, something to endure until warmth returns. But cold is also one of humanity's most valuable allies, a partner in our ongoing negotiation with entropy and decay. It's time's pause button, entropy's sleeping pill, decay's nemesis. Cold preserves our food, keeping bacterial growth at bay. By slowing the molecular machinery that powers decomposition, it stores vaccines and medicines, maintaining their potency across decades like a pharmaceutical time machine. It slows chemical reactions in ways that extend the life of everything from electronics to biological samples, turning what would be rapid degradation into something approaching immortality. In the deepest cold, chemical processes that normally proceed at breakneck speed begin to crawl, then walk, then barely move at all. This isn't just useful, it's miraculous. Cold lets us capture moments of biological time and hold them suspended, neither moving forward nor backward, but simply waiting. Cryopreservation laboratories use ultra-low temperatures to essentially stop biological clocks entirely, storing everything from embryos to rare cell lines in a state of suspended animation that would have seemed like magic to our ancestors. It's not perfect. Freezing biological tissue creates ice crystals that can damage delicate cellular structures like tiny frozen daggers, but with careful techniques and special protective chemicals called cryoprotectants, scientists can coax life to wait patiently in the cold until warmth calls it back to action. Some organisms have learned to do this naturally. Wood frogs that freeze solid each winter and thaw out in spring, none the worse for wear. Arctic ground squirrels that drop their body temperature below freezing and survive. Tardigrades that can be frozen for decades and still return to active life when warmed. The philosophy of thermal existence. So when winter wraps around you like a familiar coat, or when you feel that first chill of evening air announcing the day's transition into night, remember you're not feeling cold entering your world. You're feeling warmth leaving it, like guests departing a gathering after a wonderful evening. Your body simply notices their absence and calls it by another name. Cold isn't cruel or empty, despite our tendency to anthropomorphize it as hostile. It's natural, necessary, and in its own quiet way, profoundly beautiful. It's the universe's method of sharing energy from crowded places to spacious ones, from the bustling molecular dance floors to the quiet meditation halls of deep space, from the noisy heat of stars to the patient silence of the cosmic background. Cold is democracy at the molecular level. It's what happens when energy distributes itself evenly, when the universe moves toward thermal equilibrium, when hot spots cool down and cold spots warm up until everything reaches the same comfortable temperature. In a universe without cold, energy would pool in some places and abandon others entirely, creating pockets of impossible heat next to regions of absolute zero. Cold is the great equalizer, the patient teacher that shows energy how to share space gracefully. As we continue deeper into the cosmos tonight, carry this thought with you like a warm stone in your pocket. Cold is not the enemy of warmth, but its patient partner in the grand dance of energy that keeps the universe spinning, evolving, and dreaming new forms into existence. Without cold, there would be no temperature gradients to drive weather, no thermal differences to power ocean currents, no energy flows to sustain the complex chemistry of life itself. The universe needs its cold places as much as its warm ones. They're part of the same magnificent thermal symphony, playing different notes in the same cosmic composition. Tonight, as you rest in your own warm corner of space and time, you're participating in this ancient dance, adding your own thermal signature to the universe's ongoing conversation between hot and cold, motion and stillness, the dance of atoms and the dream of absolute zero. A stroll through the universe's temperature, from stellar fury to cosmic silence. Let's take a gentle walk through temperature, not the hurried glance at a weather app that tells you whether to grab an umbrella, but a leisurely stroll across the entire thermal landscape of existence. From the universe's hottest fires that forge the elements in your body to its most serene silences that stretch between the galaxies. Begin by imagining yourself standing at the edge of an active volcano, perhaps Kilauea in Hawaii or Stromboli in Italy, feeling the wave of heat washing over you like an ocean tide made of pure thermal energy. The molten rock bubbles and flows at around 1,200 degrees Celsius. That's hot enough to melt copper coins in your pocket, to turn ordinary sand into glass, to remind you viscerally of the incredible energy locked inside atoms when they're dancing their most frenzied dance. This is heat that has travelled from deep within the Earth, carrying stories of our planet's molten birth, of radioactive elements slowly decaying and releasing their energy over geological timescales. But terrestrial volcanism, impressive as it seems to creatures like us who consider a summer day at 35 degrees Celsius to be uncomfortably warm, is merely the gentle opening notes of the universe's thermal symphony. Now let your imagination carry you much farther, 6,000 kilometers upward through Earth's atmosphere, then 150 million kilometers across the solar system to the surface of our Sun, where temperatures hover around 5,778 Kelvin, about 5,500 degrees Celsius. Here, the familiar yellow light that warms your face on summer afternoons is born from a surface so hot that it would vaporize any earthly material instantly. The Sun's photosphere, that visible surface layer, churns and bubbles with convective cells the size of continents, each one a heat engine more powerful than all of human civilization's energy production combined. But even that's just the beginning. The gentle suburban neighborhood of cosmic temperatures, deep in the Sun's heart, where hydrogen atoms are crushed together by gravitational pressures that defy imagination, temperatures soar to 15 million Kelvin. Here, in this stellar furnace, the gentle light that allows you to read these words is born from unimaginable violence. Atoms so energetic they overcome the electromagnetic forces that normally keep them apart, merging together in nuclear fusion reactions that convert matter directly into energy, according to Einstein's famous E=mc. It's here, in these stellar cores scattered throughout the galaxy, like cosmic hearths, that the carbon in your cells, the oxygen in your lungs, the calcium in your bones, and the iron in your blood were forged. You are quite literally made of star stuff, atoms that once danced at temperatures of millions of degrees, before eventually cooling, dispersing through space, condensing into new generations of stars and planets, and finally finding their way into the biochemical miracle that is your listening, thinking, dreaming existence. But these nuclear furnaces, despite their almost incomprehensible temperatures, represent just the middle range of the universe's thermal possibilities. In the centers of the most massive stars, temperatures can reach hundreds of millions of Kelvin. During supernova explosions, the violent death throes of stars many times more massive than our Sun, temperatures briefly spike to billions of Kelvin, hot enough to forge the heaviest elements in the periodic table, hot enough to outshine entire galaxies for brief, magnificent moments. At the very extremes, in the collision zones of neutron stars or in the particle accelerators, built by human ingenuity, temperatures can momentarily approach trillions of Kelvin, conditions so extreme they recreate the universe's first fraction of a second after the Big Bang, when all of physics was compressed into a space smaller than a proton, and temperature was merely another word for the fundamental energy density of existence itself. The familiar middle, life's narrow thermal window. But these are the universe's dramatic extremes, the cosmic equivalent of standing too close to a bonfire or venturing into Arctic wilderness. Most of cosmic real estate, it turns out, prefers a much more subdued temperature range, and life as we know it exists in an even narrower thermal niche within that range. As we drift down this temperature scale like leaves falling from the hot branches of stellar physics toward the cool ground of everyday experience, We pass through the familiar, a summer day at 30 degrees Celsius when the air shimmers with heat and possibility. Room temperature at 20 degrees Celsius where most human thoughts are born. Your own body's steady 37 degrees Celsius. That remarkably precise temperature your metabolism maintains through an intricate dance of chemical reactions, circulation, and thermodynamic feedback loops. Here in this middle range, life finds its sweet spot, warm enough for the complex chemistry of biological systems to proceed at reasonable speeds, cool enough that the delicate molecular machinery of proteins and DNA doesn't tear itself apart in thermal enthusiasm. It's a range spanning perhaps 60 degrees Celsius from the Arctic bacteria that remain active at -15 degrees Celsius to the hyperthermophile organisms that thrive in hot springs at 80 degrees Celsius or even higher. This narrow band represents one of the universe's most remarkable coincidences, or perhaps inevitabilities depending on your philosophical inclination. Complex chemistry requires a delicate balance. Molecules need to be stable enough to maintain their structure, but dynamic enough to react and change. Too cold, and chemical reactions proceed too slowly to sustain the rapid metabolism that complex life requires. Too hot, and the weak bonds that hold biological molecules in their functional shapes begin to break. Proteins unfold like origami in reverse, and life's delicate architecture collapses. Water, that most essential of biological molecules, defines much of this habitable range. Its liquid phase exists from 0 degrees Celsius to 100 degrees Celsius at standard atmospheric pressure, and life on Earth has evolved to take exquisite advantage of water's unique thermal properties. Its high specific heat capacity that resists temperature changes, its ability to dissolve a remarkable variety of substances, its expansion when frozen that can burst cells, but also allows ice to float and insulate liquid water beneath. The descent into cold, where familiar physics becomes strange. Continue descending the temperature scale, and we find water freezing at 0 degrees Celsius. That familiar transition from liquid to solid that marks the boundary between comfort and challenge for most biological systems. Then comes the bite of winter air, the harsh cold of polar regions where temperatures can drop to -60 degrees Celsius or lower, where the air itself seems to crystallize and every breath becomes visible as water vapor condenses in the shock of cold. At these temperatures, the ordinary world begins to behave strangely. Metals become brittle, rubber shatters like glass. Some materials contract so much in the cold that carefully engineered structures crack and fail. The atmosphere starts to change its behavior in the depths of Antarctica. Temperatures can drop low enough that carbon dioxide begins to condense out of the air as dry ice, creating a landscape where the very air seems to be freezing. Drop further to around -196 degrees Celsius, 77 Kelvin, and we reach one of physics' dramatic thresholds. Nitrogen, which makes up about 78% of our atmosphere, gives up being a gas and becomes a liquid. This is liquid nitrogen's domain, a temperature cold enough to shatter flowers like glass, to make rubber balls bounce like superballs before shattering on the next impact, to freeze biological tissue almost instantly. Science demonstrations love this temperature for its dramatic transformations, and indeed there's something almost magical about watching ordinary objects behave in completely unexpected ways when their thermal energy drops this low. A banana becomes a hammer. A balloon shrinks to almost nothing, then returns to full size when warmed. Superconductors levitate magnets in defiance of gravity. The familiar rules of room temperature physics begin to bend and break, but we're just getting started on our journey toward true cosmic cold, toward temperatures where not just familiar materials, but physics itself begins to behave in ways that seem more like science fiction than science fact. The cosmic background chill, the universe's thermostat setting, venture out between the stars, into the vast emptiness that fills most of the universe's volume, and you'll find temperatures hovering around 2.7 Kelvin. That's approximately minus 270 degrees Celsius, cold enough to freeze air, cold enough to make liquid nitrogen seem relatively balmy. But this isn't arbitrary cold, the result of simply being far from any heat source. This is the temperature of the cosmic microwave background radiation, the faint afterglow of the Big Bang itself, still warming, if you can call it warming, every corner of space with the dying echo of creation. This background radiation represents, for most practical purposes, the baseline temperature of the universe, the coldest you can get without some very special circumstances or very clever scientific tricks. It's like a cosmic thermostat that was set to nearly absolute zero about 13.8 billion years ago and has been left running ever since, gradually cooling as the universe expands, but never quite reaching the absolute bottom of the temperature scale. What makes this background temperature so remarkable is its universality. Travel to the emptiest regions between galaxy clusters, millions of light years from any star, and you'll still encounter this same 2.7 K baseline. Hide behind the shadow of a planet to block starlight, and the cosmic microwave background still reaches you from every direction simultaneously. It's like living inside a gentle, all-encompassing warmth that connects every corner of the universe to its shared origin. Except that warmth is nearly absolute zero, the ultimate destination, absolute zero and the quantum realm. And finally, there's absolute 00 Kelvin, minus 273.15 degrees Celsius, minus 459.67 degrees Fahrenheit. This is the theoretical bottom of the temperature scale, the point where all atomic motion would cease completely, where the universe's eternal dance of particles would finally stop to catch its breath, where thermal energy would reach its absolute minimum value allowed by quantum mechanics. It's a temperature so profound it doesn't actually exist anywhere in the universe naturally, and according to the third law of thermodynamics, it never can. Because reaching absolute zero would require removing every last bit of thermal energy from a system, and the universe, it turns out, is remarkably reluctant to give up its final scraps of motion. Even in the deepest cold of intergalactic space, quantum mechanics itself provides a kind of minimum energy, zero-point energy, that prevents atoms from achieving perfect stillness. According to quantum theory, particles possess a fundamental uncertainty in their position and momentum that means they can never be completely at rest. Even at absolute zero, atoms would retain a tiny amount of motion called zero-point motion, jiggling just enough to satisfy Heisenberg's uncertainty principle. It's as if the universe has a fundamental restlessness built into its very foundations, a cosmic insomnia that prevents it from ever achieving perfect sleep. The approach to absolute zero becomes exponentially more difficult as you get closer, like trying to achieve perfect silence in a room full of whispers. You can make it quieter and quieter, but that last whisper always seems to linger. Each additional fraction of a degree removed requires exponentially more energy and more sophisticated techniques. In laboratories around the world, scientists have come tantalizingly close to this ultimate cold, within billions of a degree, using techniques that sound more like magic than physics. Laser cooling, where beams of light are used to slow atoms to a crawl. Magnetic trapping, where magnetic fields create invisible containers for ultra-cold matter. Evaporative cooling, where the hottest atoms are selectively removed, leaving behind progressively cooler collections. At these incredible temperatures, matter begins to behave in ways that seem to bend reality itself. Atoms form Bose-Einstein condensates, where individual particles lose their separate identities and merge into single unified quantum entities, matter that behaves more like a wave than a collection of particles. Liquids exhibit superfluidity, flowing without any friction whatsoever, even flowing upward against gravity, if the container geometry allows. Metals become superconductors, carrying electricity with zero resistance, allowing electrical currents to flow indefinitely without any energy source. These ultra-cold experiments reveal that absolute zero isn't just about stillness, it's a gateway to quantum mechanical behavior, so strange it challenges our fundamental intuitions about how matter should behave. It's a realm where the ordinary rules of physics give way to quantum weirdness, where particles can tunnel through barriers that should be impenetrable, where matter can exist in multiple states simultaneously until observed. The scale of it all, perspective on the thermal universe. When you step back and consider the full range of temperatures in the universe, from the hundreds of billions of degrees achieved in particle accelerators and stellar collisions, to the few nanokelvin achieved in the coldest laboratories on Earth, the span is not just staggering but almost incomprehensible. We're talking about a range of more than 15 orders of magnitude, from stellar cores where nuclei fuse in nuclear fire to laboratory chambers where atoms barely move at all. To put this in perspective, the difference between the coldest and hottest known temperatures is far greater than the difference between the smallest virus and the size of Earth. It's a range that encompasses everything from the violent birth of elements in stellar cores to the gentle approach toward perfect stillness in quantum laboratories. And somewhere in that vast thermal landscape, nestled in a remarkably narrow band that represents less than 0.001% of the total range, is you listening to these words, your body maintaining its steady 310 Kelvin 37 degrees Celsius, surrounded by air at perhaps 293 Kelvin 20 degrees Celsius, existing in what amounts to a tiny thermal oasis in a universe of extremes. The Celsius and Fahrenheit scales we use daily suddenly seem quaint when viewed against this cosmic backdrop, like measuring the ocean with a teacup or trying to capture the Milky Way in a snapshot. Kelvin, starting from absolute zero and stretching upward toward the fundamental limits of temperature, captures the full majesty of this thermal landscape in a way that honors both the frigid silence of deep space and the nuclear fury of stars. As you rest in your warm corner of existence tonight, there's something deeply comforting about knowing that even the coldest voids of space and the hottest stellar furnaces follow the same fundamental rules. They're just playing the same game of thermodynamics on different settings, with the volume turned way up for stars and way, way down for the space between galaxies. The journey toward absolute zero may be impossible to complete, asymptotic like the mathematical curves that approach, but never quite reach their limits. But every step along the way teaches us something profound about energy, motion, and the hidden architecture of reality. It's a horizon we chase not because we expect to arrive. The laws of physics themselves prevent that final achievement, but because the view along the way is breathtakingly beautiful, revealing layer after layer of the universe's elegant design. It's quantum mechanical poetry written in the language of temperature and time. The Boomerang Nebula, nature's deep freeze, and the poetry of stellar death. Let your imagination drift gently southward through the star-scattered sky, past the familiar constellations that have guided travelers and dreamers for millennia, beyond Orion's belt and the Southern Cross, until you find yourself floating in the direction of Centaurus. 5,000 light-years from the warmth of home, a distance so vast that light itself, traveling at 300 million meters per second, takes 5 millennia to bridge the gap between there and here. Here, in the vast spaces between stars where darkness has weight and silence has texture, lies one of the most extraordinary objects in the known universe, the Boomerang Nebula, nature's own deep freeze, colder than anywhere else we've ever discovered, colder even than the cosmic background radiation that bathes all of space in its ancient afterglow. Nebulae are usually places of drama and transformation, cosmic theatres where the universe performs its most spectacular acts. Some are stellar nurseries, where new suns condense from swirling clouds of dust and gas like cosmic wombs gestating the next generation of stars. Others are stellar cemeteries, the beautiful remains of stars that have lived long lives spanning millions or billions of years, burned bright enough to illuminate entire sectors of space, and finally released their outer layers in a gentle cosmic exhale, their final gift to the universe, enriching space with the heavy elements forged in their nuclear cores. The Boomerang Nebula belongs to this latter category, what astronomers call a planetary nebula, though it has nothing whatsoever to do with planets. The name is a historical accident from the 18th century, when early telescopes made these objects look like the pale disks of distant planets. In reality, there's something far more poetic, the visible souls of dying stars, their outer layers blown away by stellar winds and illuminated by the remaining white dwarf core, like cosmic lanterns powered by nuclear memory. What makes this particular nebula so special, so uniquely magnificent in its chill, is its temperature, just 1 Kelvin above absolute zero. That's minus 272.15 degrees Celsius. Colder even than the baseline temperature of empty space itself, colder than liquid helium, colder than anything nature produces anywhere else in the observable universe. This seems impossible at first, like discovering a shadow darker than midnight, or finding silence quieter than the absence of sound. Space, after all, is already about as cold as nature allows, sitting at a frigid 2.7 Kelvin, thanks to the cosmic microwave background radiation, that ancient whisper of warmth left over from the Big Bang, still reaching across billions of years to connect every corner of existence to its shared origin. How can anything become colder than the universe's own background temperature? The birth of ultimate cold, a star's final magic trick. The answer lies in the Boomerang Nebula's remarkable origin story, a tale of stellar death that reads like physics poetry. At its heart sits a dying star, now in its twilight years after burning for perhaps billions of years, which began ejecting its outer layers in a process both violent and beautiful. But this wasn't a gentle, gradual release like an old person, slowly breathing out. The gas is streaming outward at over 500,000 kilometers per hour. Imagine an elderly star suddenly transforming into a cosmic hurricane, expelling its atmosphere at speeds that make supersonic jets look like they're standing still. To put this in perspective, at such speeds you could travel from Earth to the Moon in about 45 minutes. This isn't just fast, it's almost incomprehensibly rapid. Fast enough that the expanding gas doesn't have time to equilibrate with the surrounding space. Fast enough to create conditions that shouldn't exist in nature. When gas expands this rapidly into the near vacuum of space, it cools dramatically through a process called adiabatic expansion, the same principle that makes compressed air feel cold when you release it from a spray can, or how your refrigerator works to keep your food fresh. Expanding gas naturally drops in temperature as its thermal energy spreads across a larger and larger volume, like spreading a fixed amount of butter across an ever larger slice of bread. But the Boomerang Nebula takes this cooling to an extreme that challenges our understanding of what's possible in nature. The expansion is so rapid and so complete that the gas temperature plummets below even the 2.7 Kelvin background of space itself, achieving what seems like a thermodynamic miracle. How does it manage this seemingly impossible feat? The answer lies in the nebula's unique geometry and density. The dense cloud of expanding gas acts like a natural thermal blanket, shielding itself from the faint warmth of the cosmic microwave background radiation. Inside this cocoon of stellar breath, protected from the universe's baseline temperature, the gas can cool to temperatures lower than the surrounding space, a pocket of deeper cold floating in the already frigid sea of the cosmos, like finding an ice cube in a freezer that's somehow colder than the freezer itself. The expanding gas also carries away energy through radiation, glowing faintly in infrared wavelengths as it cools. This radiative cooling, combined with the rapid expansion, creates a runaway refrigeration effect, where the gas becomes its own cosmic air conditioner, cooling itself to temperatures that approach the theoretical limit of coldness. Discovery of the cosmic deep freeze, when radio telescopes heard silence. The Boomerang Nebula remained hidden from human eyes until the 1980s, when radio astronomers, those patient listeners to the universe's quieter voices, noticed something peculiar in their data. This object was emitting far less radiation than expected from a typical planetary nebula, showing the telltale signature of something extraordinarily cold. In radio astronomy, objects typically reveal themselves by their thermal emission, the radio waves they give off due to their temperature. Hot objects shine brightly in radio wavelengths, while cool objects whisper, but the Boomerang Nebula was barely whispering at all, so thermally quiet that it almost disappeared from radio surveys entirely. It was like trying to hear a conversation in a library, where even the librarians were speaking in sign language. Further observations with increasingly sophisticated instruments confirmed what seemed impossible. Here was a natural refrigerator, floating in space, achieving temperatures that human technology struggles to reach even in the most sophisticated laboratory environments on Earth. Ground-based telescopes, space-based observatories, and radio interferometers all agreed this object was pushing the boundaries of how cold the universe could naturally become. Early ground-based observations gave the nebula its name, as its structure appeared to resemble a boomerang in mid-flight when viewed through terrestrial telescopes. The name stuck even as better observations revealed more complex structure, because sometimes the universe deserves to keep a little poetry in its nomenclature. Later, the exquisite detail provided by the Hubble Space Telescope revealed something even more beautiful than a simple boomerang. An hourglass-shaped cloud with symmetric wings of gas streaming outward in opposite directions, like a cosmic butterfly spreading its wings in the darkness. A butterfly made entirely of frost and starlight, its wings sculpted by stellar winds and shaped by magnetic fields into patterns of almost mathematical perfection. The structure suggests that the dying star at the nebula's heart is actually a binary system, two stars orbiting each other in their final dance. As one star expands and dies, its companion's gravitational influence shapes the outflowing gas into these elegant symmetric patterns, creating art from astrophysics, beauty from the fundamental forces of nature. The poetry of stellar death, when fire becomes ice. There's something deeply poetic about the Boomerang Nebula's existence, something that speaks to the universe's capacity for surprise and transformation. Here we have a star's final breath transformed not into the usual fire or explosion that characterizes most stellar deaths, but into the purest expression of cold the universe has ever naturally achieved. Stars are supposed to burn, to radiate energy across space, to fill the cosmos with heat and light. They're the universe's furnaces, its sources of warmth and energy, and life-sustaining radiation. For billions of years, the star at the heart of the Boomerang Nebula did exactly that: fused hydrogen into helium, helium into carbon, carbon into heavier elements, maintaining the nuclear fires that define stellar existence. Yet here is one choosing a different path for its finale, ending not in a blaze of glory like a supernova, not in the gentle warming glow typical of most planetary nebulae, but in an exhalation of silence so profound it creates the coldest known place in the universe. It's as if the star decided to whisper its goodbye instead of shouting it, to leave behind not heat but its absence, not fire but the memory of ice. If you could somehow stand within the Boomerang Nebula, setting aside for a moment the complete absence of anything to stand on, anything to breathe, or any way to survive the cold that would freeze your atoms solid in milliseconds, you would experience something approaching perfect stillness. Not the peaceful quiet of a calm evening when the world settles into sleep, but the profound silence that comes when thermal motion itself nearly ceases to exist. You would be surrounded by gas so cold that its atoms barely move, creating a kind of crystallized space matter holding its breath in the darkness, waiting for some cosmic alarm clock to wake it from its frozen dreams. The hydrogen and helium atoms around you would be moving so slowly that their thermal velocities would be measured in mere meters per second, rather than the hundreds of meters per second, typical of room temperature gases. In this environment, the familiar rules of chemistry and physics begin to break down. Chemical reactions that occur rapidly at room temperature would proceed so slowly they might take geological ages to complete. Atoms would rarely collide with enough energy to form or break chemical bonds. It would be like living inside a photograph of the universe, where time itself has nearly stopped and change becomes a theoretical concept rather than a practical reality. A fleeting wonder, the impermanence of perfection. This extraordinary cold won't last forever. Indeed, on cosmic timescales, it's already a brief and fleeting phenomenon, as the gas continues to expand and thin over thousands of years, as light from distant stars gradually penetrates the shroud, as the cosmic microwave background radiation slowly but inexorably warms the expanding cloud. The temperature will gradually rise. The Boomerang Nebula will eventually warm back up to the standard cosmic chill of 2.7 Kelvin, joining the thermal background of the universe like a unique voice, eventually blending back into the cosmic choir. This deep freeze is a temporary masterpiece, a brief moment in cosmic time when conditions aligned perfectly to create something that pushes against the fundamental limits of how cold nature can become. But temporary in astronomical terms still means thousands of human lifetimes. The nebula will maintain its record-breaking cold for millennia to come, long enough for countless generations of astronomers to study its properties, to marvel at its impossible temperature, to learn from its lessons about thermodynamics and stellar death. The star at its heart will continue its own evolution, eventually becoming a white dwarf, a stellar ember no larger than Earth, but containing more mass than our Sun, slowly cooling over billions of years as it radiates away its remaining heat into the cosmos. The nebula itself will gradually disperse, its gas eventually mixing with the interstellar medium, carrying its complement of heavy elements to seed future generations of stars and planets. Lessons from the cosmic freezer. What the Boomerang teaches us. The Boomerang Nebula stands as proof that the universe still has surprises to offer, even after centuries of astronomical observation and theoretical understanding. In a cosmos filled with burning stars and violent explosions, with black holes and gamma-ray bursts and neutron stars spinning hundreds of times per second, here is a place of utter tranquility, where a dying star's final gift to the universe is not heat or light, but the deepest, most perfect cold nature has ever achieved. It reminds us that extreme conditions don't always require extreme violence. Sometimes the most remarkable phenomena arise not from cosmic catastrophes, but from subtle interactions between radiation and thermodynamics. The Boomerang Nebula achieves its record-breaking cold not through some exotic physics or extreme environment, but through the patient application of fundamental physical principles, adiabatic expansion, radiative cooling, and thermal isolation working together in perfect harmony. For scientists studying ultra-low temperatures, the Boomerang Nebula serves as a natural laboratory where conditions exist that we can barely achieve on Earth even with our most sophisticated equipment. It's a cosmic test case for our understanding of matter under extreme conditions, a natural experiment in approaching absolute zero that teaches us about phase transitions, quantum behavior, and the fundamental limits of thermal physics. It drifts through space like a whispered lullaby, a reminder that even in death, stars can create beauty beyond imagination. And somewhere, 5,000 light-years from your warm bed, that beauty continues its slow, cold dance among the stars, the universe's own meditation on silence, stillness, and the elegant physics of letting go. The Boomerang Nebula is more than just a cosmic curiosity or a record holder in the book of extreme temperatures. It's a philosophical statement about the nature of endings, a demonstration that conclusions need not be violent or dramatic to be profound. Sometimes the most powerful finale is the gentlest one, a star's decision to end not with an explosion, but with an exhalation, not with fire, but with the purest expression of cold the universe has ever known. As you rest tonight in your own warm corner of space and time, carry with you the image of this cosmic winter, a place where stellar death becomes stellar art, where the end of one story becomes the beginning of another, where the universe demonstrates once again that its capacity for beauty extends even to its coldest, most silent places. The ancient whisper, cosmic microwave, background and the universe's memory. Close your eyes for a moment and picture the very beginning of everything, not just Earth or our solar system, not even our galaxy, but the entire universe itself. Imagine a time 13.8 billion years ago, when all of space was compressed into something smaller than the period at the end of this sentence, blazing with unimaginable heat and density that defies every intuition we have about how matter should behave. There was no darkness then, no cool emptiness, no quiet corners where thoughts could form or dreams could take shape. Everything that would ever exist, galaxies spiraling through space, stars burning in their nuclear furnaces, planets orbiting in gravitational ballet, the air you're breathing right now, the carbon atoms in your DNA, the calcium in your bones, all of it was packed together in a searingly bright, chaotic symphony of pure energy, hotter than the core of the most massive stars, denser than the heart of neutron stars, existing in a state so extreme that the familiar laws of physics themselves were still learning how to operate. This was the universe's infancy, its first moment of existence when space and time themselves were being born from, well, from whatever exists before existence itself. It was a moment of such intensity that temperature and density were essentially infinite, when the concepts of hot and cold had not yet learned to distinguish themselves, when all of physics was compressed into a singularity that contained the potential for everything that would ever be. But the universe, like all things of great passion and intensity, began to cool as space expanded, not expanding into something, but creating the very concept of something to expand into. The incredible energy of creation began to spread across larger and larger volumes, like taking a photograph and stretching it until the individual pixels become visible, except here, the pixels were the fundamental particles of matter and energy themselves. The moment of first light, when the universe learned transparency, around 380,000 years after that initial moment, a mere blink in cosmic terms, but an eternity compared to the Planck timescales on which quantum mechanics operates. Something remarkable and beautiful happened. The universe had expanded and cooled just enough from trillions of degrees down to a mere few thousand for electrons to settle into stable orbits around protons, forming the first neutral hydrogen atoms in cosmic history. This seemingly modest event, this quiet atomic settling, had the most profound consequences imaginable. For the first time since the Big Bang, light could travel freely through space without being immediately absorbed or scattered by free electrons. Before this moment, the universe was opaque, filled with a hot plasma of charged particles that absorbed and re-emitted photons constantly, like trying to see through a thick fog made of pure energy. The universe, you might say, cleared its throat and became transparent. It was as if cosmic cataracts had been suddenly removed, allowing light to stream freely across space for the first time. This moment is called recombination, though it's really more like combination, the first time electrons and protons had ever gotten together to form complete atoms. That first light, the afterglow of creation itself, The photons that had been bouncing around in the primordial plasma since the first moments after the Big Bang suddenly found itself free to travel, and it has been traveling ever since, carrying with it the thermal signature of the universe at the moment of recombination, like a cosmic message in a bottle thrown into the ocean of space-time 13.8 billion years ago. We call this ancient light the cosmic microwave background, or CMB, and it surrounds you right now as you listen, invisible but ever present, like the universe's own lullaby humming at frequencies your ears cannot detect, but your radio receivers can capture with exquisite precision. The temperature of memory, how the universe remembers its youth. This ancient light carries with it a temperature, 2.725 Kelvin, just a whisper above absolute zero, about minus 270.425 degrees Celsius, to be precise. That might not sound like much warmth, barely enough to register on any thermometer designed for human use, but it represents something profound and beautiful, the baseline temperature of the entire universe, the cosmic thermostat setting that has been slowly declining for nearly 14 billion years. It's the minimum natural temperature that space itself maintains everywhere you might travel among the stars, a thermal floor beneath which the universe simply does not go without very special circumstances. Every cubic centimeter of space, from the emptiest voids between galaxy clusters to the space between atoms in your own body, maintains this same temperature through the presence of these ancient photons. When the cosmic microwave background first separated from matter, all those billions of years ago, when photons first gained the freedom to travel without constant absorption and re-emission, it was blazing hot around 3000 Kelvin, hot enough to glow with visible light, bright enough that if you could have existed then and looked around, the entire universe would have appeared to be glowing with the warm orange light of heated metal, like living inside a cosmic furnace. But as the universe expanded, that light stretched along with space itself, growing longer in wavelength and cooler in temperature, in one of the most elegant demonstrations of the relationship between cosmology and thermodynamics. The expansion of space literally stretched the wavelengths of these photons, shifting them from the brilliant visible spectrum down through infrared, then far infrared, and finally to the gentle microwaves we detect today. It's like listening to the Doppler shift of a train whistle, except instead of the train moving away from you, space itself is expanding and carrying the light along with it, stretching its wavelengths like an accordion being slowly pulled apart. If the universe had stopped expanding billions of years ago, this relic radiation would still be blazing in our sky like a cosmic furnace, making the night sky glow with the brightness of molten metal. Instead, it has cooled alongside the cosmos itself, becoming a faint whisper of warmth that fills every corner of existence, a thermal fossil that preserves the memory of the universe's hot youth in the same way that light from distant stars preserves the history of stellar evolution. An accidental discovery, when engineers found the echo of creation. The cosmic microwave background was discovered quite by accident in 1965 by two radio engineers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, in one of the most beautiful cases of serendipity in the history of science. They weren't looking for the echo of creation, they were simply trying to eliminate mysterious static from their sensitive radio antenna, static that was interfering with their attempts to bounce radio signals off communication satellites. They were meticulous in their approach. These two engineers faced with an annoying technical problem. They tried everything to solve their noise issue. They cleaned the antenna's metal surfaces until they gleamed. They checked and rechecked all their electronic equipment. They even discovered and evicted a pair of nesting pigeons who had taken up residence in the antenna's horn-shaped receiver and had contributed their own substantial biological deposits to the cleanliness problem. But the static persisted, a gentle hiss that seemed to permeate all of space equally, no matter which direction they pointed their equipment. It was there during the day and at night, in summer and winter, when they pointed toward the galactic center with its abundance of stars, and when they pointed toward the emptiest regions of sky. It was a noise that seemed to have no earthly source, no obvious explanation, no way to eliminate it through any amount of careful engineering. What they had discovered, quite without intending to, was the echo of creation itself, the stretched and cooled radiation from the universe's hot birth, still reaching across billions of years to whisper its ancient story to anyone with sensitive enough equipment to listen. For this serendipitous find, this accidental eavesdropping on the universe's oldest conversation, they were awarded the Nobel Prize in Physics in 1978. Their discovery gave humanity its first direct glimpse of the universe's infancy, the first empirical evidence for the Big Bang Theory, the first proof that the cosmos really did have a hot, dense beginning from which it has been expanding and cooling ever since. It was like finding baby pictures of the universe itself, photographs taken when the cosmos was just 380,000 years old, a newborn by astronomical standards. Mapping the baby pictures of everything, satellites as time machines. Since that accidental discovery, scientists have built increasingly sophisticated instruments to study this cosmic background radiation in exquisite detail, creating what are essentially baby pictures of the entire universe. Maps showing the tiny temperature fluctuations in that ancient afterglow with precision that would have seemed like magic to earlier generations of astronomers. Satellites like COBE, the Cosmic Background Explorer in the 1990s, first detected the subtle variations in the CMB temperature across the sky, variations so small they had to be measured in millionths of a degree. Map, the Wilkinson Microwave Anisotropy Probe, in the 2000s created detailed maps of these fluctuations with unprecedented precision, and Planck, the European Space Agency's Cosmic Microwave Background Mission that operated through the 2010s, measured these ancient temperature variations with such accuracy that scientists can now determine fundamental properties of the universe, its age, its geometry, its composition, to several decimal places. These aren't dramatic variations, just ripples of about 1 part in 100,000, like gentle waves on an otherwise perfectly still pond, barely detectable above the cosmic background's remarkable uniformity. But within those subtle fluctuations lies the seed pattern for everything that came after, the slight density variations that would eventually grow through the patient influence of gravity, acting over millions and billions of years, into galaxies, galaxy clusters, the large-scale structure of the cosmos itself. By studying these ancient ripples with the precision of cosmic archaeologists, scientists can determine not just how old the universe is, 13.8 billion years, but what it's made of, about 5% ordinary matter, 27% dark matter, and 68% dark energy. How fast it's expanding, the Hubble constant, whether space is curved or flat, remarkably flat, and even glimpses of its ultimate destiny billions of years in the future. The cosmic microwave background has become our most precise baby picture of the universe, more detailed and informative than any photograph ever taken. It's a snapshot of the cosmos when it was just beginning to become the structured, galaxy-filled universe we see today, caught at the moment when it first became transparent and light gained the freedom to travel. Your connection to ancient light, bathed in the afterglow of creation, here's something beautiful and profound to contemplate as you rest in your warm corner of space and time. That cosmic microwave background radiation isn't just some distant phenomenon that astronomers study with exotic equipment. It's surrounding you right now, at this very moment, passing through your room, through your body, connecting you directly to the universe's earliest moments with invisible threads of ancient light. If you remember old analog televisions with their grainy static when no channel was tuned in, that dancing snow of black and white pixels that filled the screen, A small percentage of that visual noise was actually the cosmic microwave background radiation making itself known. About 1% of that television static was the visual signature of creation itself flickering on your screen. Photons that had been traveling for nearly 14 billion years to reach your living room and add their ancient whisper to the electronic noise of modern technology. Every second, approximately 400 million cosmic microwave background photons pass through each square centimeter of your body. You are constantly bathed in this ancient light, these messengers from the universe's infancy, carrying information about the cosmos when it was younger than a human lifetime, when the first atoms were forming, when the stage was being set for everything that would follow. This radiation is remarkably uniform across all directions in space, filling the cosmos so evenly that if you could somehow travel to the emptiest regions between galaxy clusters, millions of light years from any star or galaxy, you would still encounter this same 2.725 Kelvin background temperature. It's a limit imposed by history. The afterglow of creation itself still has a say in how cold the present can become. The cosmic microwave background is proof that we're all connected to the same origin story, that every corner of the observable universe shares this common thermal heritage. It's like discovering that everyone in the world is distantly related through a common ancestor, except here, the common ancestor is the Big Bang itself, and the family resemblance is carried by photons that have been traveling since the universe was in its cosmic infancy. A gentle omnipresence, the universe's eternal nightlight. What makes the cosmic microwave background so remarkable and so different from other forms of radiation is its omnipresence. Unlike sunlight, which streams toward you from one particular direction and creates shadows and day and night, this ancient radiation surrounds you completely. It doesn't beam at you from any specific source. It envelops you like a warm bath, coming from literally everywhere at once. You can't hide from it or block it out easily, because it's approaching from every direction simultaneously. Up and down, left and right, front and back. It's the light of the universe itself, stretched into a gentle, all-encompassing glow that connects every point in space to the shared moment when the cosmos first became transparent. This radiation carries within it the polarization patterns and spectral fingerprints of the early universe's structure, allowing scientists to peer back in time further than any optical telescope looking at the most distant galaxies could manage. It's like having a preserved recording of the universe's first song, played at frequencies so low they've become a cosmic hum, but containing information about the initial conditions that gave rise to everything we see around us today. The tiny variations in the CMB temperature across the sky, those millionths of a degree fluctuations that satellites can measure, represent the quantum fluctuations that existed in the first fraction of a second after the Big Bang, stretched by cosmic inflation to cosmic proportions. They're the fossilized remains of quantum uncertainty made manifest on the largest scales imaginable, proving that the universe we inhabit today emerged from quantum mechanical origins. The comfort of cosmic connection, always surrounded by ancient light. As you settle deeper into comfort tonight, there's something profoundly soothing about knowing that this gentle radiation surrounds you always, a cosmic nightlight that has never been turned off since the universe first became transparent. 13.8 billion years ago, no matter how vast space becomes as the universe continues its expansion, no matter how far galaxies drift apart over cosmic time, this soft background glow remains, connecting every corner of existence to its shared origin. The cosmic microwave background is the universe's way of saying, I remember my beginning, and I'm still here. It's proof that we're all participants in a story much larger and older than ourselves, bathed constantly in the afterglow of the very event that made our existence possible. Every atom in your body, every thought in your mind, every dream you'll dream tonight, exists against this backdrop of ancient light. When astronomers look at the cosmic microwave background, They're seeing the universe as it was when it was just 380,000 years old, practically newborn by cosmic standards. But those photons they're detecting have been traveling ever since, witnesses to the entire history of cosmic evolution, present at the formation of the first stars, the birth of the first galaxies, the synthesis of the heavy elements, the formation of planetary systems, the emergence of life. The CMB photons reaching us now have seen it all, and they carry in their wavelengths and polarizations the accumulated wisdom of cosmic history. They're like cosmic messengers who have been traveling since the dawn of time to bring us news of our origins. Patient couriers carrying the universe's birth certificate across billions of years to deliver it personally to our radio telescopes. So, as you drift towards sleep tonight, wrapped in your own warm corner of space and time, know that you're also wrapped in something far grander, the faint but enduring warmth of creation itself, still humming its ancient lullaby across the cosmos. The cosmic microwave background is still connecting this moment to the dawn of everything that ever was or ever will be, still whispering the universe's oldest story to anyone quiet enough to listen. It's a reminder that we exist not in isolation, but as part of an unbroken chain of cosmic events stretching back to the very beginning of time itself. Tonight, as your consciousness begins its own daily journey toward the quiet mystery of sleep, you're surrounded by light that has been traveling since consciousness itself was nothing more than a possibility written in the quantum fluctuations of the primordial universe. The cosmic microwave background is proof that the universe has a memory, that the past is not gone but transformed, carried forward in the wavelengths of ancient light. And in detecting this radiation, in mapping its subtle variations, in learning to read the story it tells, humanity has achieved something remarkable. We've learned to hear the universe's own lullaby, the gentle song it has been singing to itself since the moment it first learned to let light travel freely through space. Sleep well, knowing you're cradled, not just in the warmth of your immediate surroundings, but in the ancient afterglow of creation itself, a cosmic embrace that connects you to the beginning of everything, a gentle reminder that you are, quite literally, made of star stuff and surrounded always by the light of Genesis. The spaces between might interstellar cold and the poetry of emptiness. Drift with me now into the vast emptiness between stars, where distances are measured not in kilometers or even millions of kilometers, but in light years, units so large they strain human comprehension, where the darkness is so complete it has weight and substance, and where cold takes on a meaning far removed from any earthly winter you've ever experienced. This is interstellar space, not quite empty, as we'll discover, but so sparse, so profound in its near-nothingness, that calling it nearly empty barely does justice to its extraordinary quietude. It's a realm where the concept of emptiness becomes almost philosophical, where the absence of matter creates its own presence, where the spaces between things become more significant than the things themselves. If you could float through these regions without the protection of a spaceship, and let's imagine, for the sake of our gentle journey into impossibility, that your atoms somehow cooperate with this scenario and don't instantly freeze into crystalline perfection, you would find yourself in a place where temperature hovers steadily around 2.7 Kelvin. That's approximately minus 270.45 degrees Celsius, just a few degrees above absolute zero, maintained not by any local heat source, but by the cosmic microwave background radiation we explored in our previous chapter. That ancient afterglow of the Big Bang, still providing the universe's baseline warmth after nearly 14 billion years of cosmic expansion. But what makes interstellar space truly extraordinary? What gives it its character of profound meditation and cosmic contemplation isn't just its cold, it's its emptiness. Its emptiness so complete it becomes a thing unto itself, a presence made of absence, a fullness of void that teaches us new meanings for the word nothing. The mathematics of emptiness, counting atoms in the void. In each cubic centimeter of interstellar space, a volume about the size of a sugar cube, small enough to hold in your palm, you might find one or two hydrogen atoms floating in splendid isolation, just one or two. Sometimes none at all. To put this in perspective, that might make your drowsy mind reel with the implications. The air you're breathing right now as you listen contains about 25 billion molecules in that same small volume. Let that settle into your consciousness for a moment. 25 quintillion molecules in room temperature air versus one or two atoms in the space between stars. It's a difference so vast that it challenges our ability to find appropriate metaphors. If the air around you were a bustling city with every molecule representing a person, then interstellar space would be like finding one or two people scattered across an area the size of several continents. You could scoop up a sphere of interstellar space the size of Earth, 13,000 kilometers in diameter, vast enough to contain entire mountain ranges and oceans and continents, and barely gather enough matter to fuel a modest campfire. The entire sphere would contain less mass than a small asteroid, less substance than the metal in a paperclip, less matter than you exhale in a single breath. This is emptiness so profound it becomes almost mystical. It's not the familiar emptiness of a vacant room, where air still fills the space between walls. It's not even the emptiness inside a vacuum flask, where sophisticated pumps have removed most of the air, but millions of molecules per cubic centimeter still remain. This is emptiness approaching the theoretical limit, where matter becomes so sparse that atoms might travel for years, decades, even centuries before encountering another atom to interact with. The slow dance of isolated atoms, motion in the void. In this profound near vacuum, the few atoms that do exist move with a stately, almost ceremonial pace. Unlike the frenzied collisions and constant interactions that characterize matter at room temperature and pressure, these isolated hydrogen atoms drift through space like cosmic hermits, each following its own trajectory through the darkness, rarely encountering neighbors to exchange energy with. The temperature of 2.7 Kelvin means these atoms move with average speeds of only about 260 meters per second, fast by human standards, but remarkably sedate compared to the 500 meters per second that characterizes room temperature hydrogen. More importantly, they move through space so empty that they almost never collide with anything. An individual hydrogen atom in interstellar space might travel for thousands of years before bumping into another atom. This creates a kind of physics that doesn't exist anywhere else in our daily experience. Matter so isolated that each atom is essentially alone with its thoughts, uninfluenced by neighbors, following the pure mathematics of celestial mechanics, as it responds only to the gravitational pull of distant stars and the gentle pressure of starlight itself. In this environment, the familiar concepts of temperature and thermal equilibrium take on almost philosophical meanings. Temperature, after all, is usually defined in terms of the average kinetic energy of particles in thermal contact with each other. But what does temperature mean when particles almost never make contact? The 2.7 K temperature of interstellar space is really the temperature at which these atoms would be in equilibrium with the cosmic microwave background radiation, not with each other, but with the photons of ancient light that fill all of space. The subtle architecture of the void, hidden structure in apparent nothingness. Yet even this profound emptiness has structure, organization, a kind of cosmic architecture that emerges from the interplay between gravity, stellar winds, and the ancient history of star formation and stellar death. Interstellar space isn't uniformly empty. It's organized into regions of different density, temperature, and composition, like invisible neighborhoods in the cosmic city. There are the cold, dense molecular clouds where new stars are born, regions where the density might climb to thousands of atoms per cubic centimeter, practically crowded by interstellar standards. These stellar nurseries are the universe's maternity wards, where gravity slowly gathers matter over millions of years until nuclear fusion ignites and new suns are born. Then there are the hot, thin regions carved out by stellar winds and supernova explosions, bubbles of space heated to millions of degrees, but so tenuous that they contain fewer atoms than the coldest parts of interstellar space. These hot zones create a kind of cosmic Swiss cheese, cavities in space blown clear by the violent deaths of massive stars, regions where the few atoms present move at tremendous speeds but encounter each other so rarely that the space feels empty despite its high temperature. Between these extremes lies the general interstellar medium, the baseline emptiness that fills most of the space between stars, with its 1 or 2 atoms per cubic centimeter, its patient 2.7 Kelvin temperature, its profound quiet that has persisted for billions of years. Magnetic fields in the darkness, the universe's invisible infrastructure. Perhaps most remarkably, this near-empty space is threaded with magnetic fields, invisible lines of force that stretch between the stars like a cosmic nervous system, carrying information and energy across distances that dwarf any earthly comparison. These magnetic fields, typically about a millionth the strength of Earth's magnetic field, nevertheless play crucial roles in the physics of interstellar space. They guide the motion of the few charged particles that exist in the void, creating invisible highways along which cosmic rays travel from star to star. They influence the formation of new stars by helping to compress molecular clouds or by preventing their collapse, acting as a kind of cosmic midwifery that determines when and where new suns will be born. Most beautifully, these magnetic fields can become visible when they interact with the light from distant stars, creating polarization patterns that allow astronomers to map the invisible architecture of supposedly empty space. It's like discovering that the darkness between stars has its own geography, its own topology, its own hidden landscapes that can only be seen with the most sophisticated instruments and techniques. The speed of silence, how information travels in the void. In this profound emptiness, information and energy travel at their fundamental speed limits. Light crosses interstellar distances at exactly 299,792,458 meters per second. The speed of light in vacuum, the universal speed limit that represents the maximum rate at which cause and effect can propagate through space-time itself. But unlike light traveling through air or water or glass, photons crossing interstellar space encounter essentially no resistance, no absorption, no scattering from matter. They travel in perfectly straight lines across distances so vast that they carry information about events that happened millions or billions of years ago. The starlight reaching your eyes tonight left its source years, decades, or centuries ago, carrying news of stellar events across the emptiness with perfect fidelity. This creates a kind of cosmic archaeology, where the present moment contains information from throughout the history of the universe. The light from distant galaxies tells us about the cosmos, as it was billions of years ago, while the light from nearby stars brings news from years or decades past. We live in a universe where the present is constantly being informed by messages from the past, all delivered through the patient emptiness of interstellar space. Dust in the darkness, the universe's smallest architects. Even in this profound emptiness, there exists something smaller than atoms that plays an outsized role in cosmic evolution: interstellar dust. These are grains typically smaller than the particles in cigarette smoke, made of carbon, silicon, and metals forged in the hearts of dying stars and dispersed into space by stellar winds and supernova explosions. There might be only a few thousand of these dust grains in each cubic meter of interstellar space, a density so low it would represent a perfect vacuum by any earthly standard. Yet these tiny particles floating in the darkness between stars serve as the seeds for planets, the nuclei around which matter can condense to form the solid worlds where life might arise. Interstellar dust also plays a crucial role in the chemistry of space, providing surfaces where atoms can meet and combine to form molecules. In the profound cold and emptiness between stars, gas phase chemical reactions proceed so slowly they're almost non-existent. But on the surfaces of dust grains, atoms can stick and accumulate, allowing complex molecules to form over cosmic timescales. Water, methanol, ammonia, and even complex organic molecules have been detected in interstellar space, all formed through the patient chemistry that occurs on dust grain surfaces floating in the cosmic void. These molecules eventually become incorporated into new stars and planetary systems, seeding them with the chemical diversity necessary for the eventual emergence of life. The loneliness of light, photons traveling through eternity. Consider the loneliness of a photon born in the nuclear furnace of a distant star, traveling through this interstellar emptiness for thousands of years before finally reaching Earth. For most of its journey, it encounters essentially nothing, no matter to interact with, no obstacles to navigate around, no companions to travel with. It maintains its energy and direction with perfect constancy, a quantum messenger carrying information across the void with mechanical precision. Its wavelength remains unchanged, its polarization preserved, its quantum state unaltered by the emptiness it traverses. It's like a letter written in light, sealed at the moment of its creation, and delivered unchanged across cosmic distances and cosmic time. When that photon finally reaches your eye tonight, when you look up at a star twinkling in the darkness, you're receiving a message that has traveled through this profound emptiness, carrying information about nuclear processes that occurred in stellar cores years or decades or centuries ago. The twinkling you see isn't a property of the star itself. It's caused by turbulence in Earth's atmosphere, the last few kilometers of the photon's journey after it has traveled peacefully through interstellar space for most of its existence. The philosophy of cosmic emptiness, what the void teaches us. There's something deeply contemplative about interstellar space, something that challenges our earthbound notions of what existence means. Here is a realm where matter is so sparse that the concept of nothing takes on new meaning, where emptiness becomes not just the absence of something, but a presence unto itself. In our daily lives, we're surrounded by matter, air to breathe, surfaces to touch, objects to interact with. We live in a world of constant molecular contact, where atoms are always bumping into each other, where chemistry is always happening, where change and interaction are the norm. But in interstellar space, isolation is the rule, patience is measured in millennia, and change happens on timescales that dwarf human history. This emptiness teaches us about the true scale of the universe, about the vast distances that separate the islands of matter we call stars and planets. It reminds us that most of the universe's volume is not filled with the bustling activity of stellar cores or the complex chemistry of planetary surfaces, but with this patient, persistent near-nothingness that serves as the stage upon which all cosmic drama unfolds. Yet this apparent emptiness is not sterile or meaningless. It's the medium through which information travels, the space through which gravity operates, the reservoir from which new stars and planets will eventually form. It's connected to everything else in the universe through invisible threads of gravitational influence, magnetic fields, and the constant flow of energy and matter that cycles between stars and the interstellar medium. The comfort of cosmic perspective, finding peace in the vast. As you rest tonight in your warm, matter-filled corner of the universe, surrounded by air thick enough to breathe and surfaces solid enough to support you, there's something paradoxically comforting about knowing that most of space is this profound, patient emptiness. It provides a kind of cosmic perspective that puts our earthly concerns in context. The interstellar void reminds us that the universe is mostly a quiet place, that the violent events we associate with space, supernova explosions, black hole mergers, stellar collisions, are dramatic precisely because they stand out against this backdrop of gentle emptiness. Most of space, most of the time, is engaged in this slow, patient dance of nearly nothing, this meditation on the meaning of existence at its most sparse and fundamental level. There's something deeply peaceful about this vision of the universe as mostly empty, mostly quiet, mostly engaged in the slow work of simply existing across vast scales of space and time. It suggests that patience and persistence are fundamental cosmic virtues, that the universe itself practices a kind of meditation on the meaning of being. The atoms drifting through interstellar space are like cosmic monks, each following its own contemplative path through the darkness, occasionally encountering others, but mostly content to exist in solitary communion with the quantum vacuum, the zero-point energy that ensures that even emptiness is never truly empty at the deepest level. The promise of future fullness, what emptiness becomes. This interstellar emptiness is not permanent or sterile. Over cosmic timescales, millions and billions of years, gravity slowly gathers this sparse matter, concentrating it into the dense molecular clouds where new stars are born. The emptiness between stars is constantly being recycled, constantly being gathered up and concentrated, constantly being transformed from void into substance. The atoms floating in interstellar space today may eventually become part of a new star, contributing their small mass to a new nuclear furnace that will burn for millions or billions of years, or they may become part of a planet, incorporated into rock or atmosphere, or eventually into the complex chemistry of life itself. This gives the interstellar void a kind of temporal richness that belies its present emptiness. It's not just void, it's potential. It's the raw material from which future worlds will be built. The profound emptiness you're contemplating is pregnant with possibility, filled with the promise of stars and planets, and perhaps even life that will emerge from its patient darkness over the fullness of cosmic time. So, as you drift towards sleep tonight, carry with you this image of the spaces between stars, not as empty or cold or hostile, but as patient, profound, and full of potential. The interstellar void is the universe's way of creating space for possibility, of providing room for the future to unfold, of practicing the cosmic patience that allows matter and energy to dance their slow dance across the stage of existence. In the profound quiet of interstellar space, in its patient, cold, and gentle emptiness, we find not the absence of meaning, but one of its deepest expressions. The universe's commitment to providing space and time for complexity to emerge, for stars to be born, for planets to form, and for consciousness itself to eventually arise and contemplate the very emptiness from which it came. The spaces between stars are not empty. They're full of possibility, pregnant with potential, rich with the patient promise that even the most profound void can give birth to wonder, to complexity, to the kind of consciousness that can lie in a warm bed on a small planet and dream about the vast, gentle emptiness that connects all things across the cosmos. Rest well in your tiny corner of this vast universe, knowing that you exist not despite the emptiness that surrounds us, but because of it, because the universe had the patience to create space and time enough for matter to organize itself into the remarkable complexity that includes your listening, dreaming, wondering mind. Laboratory cold, where humans touch absolute zero. Let us drift now from the natural cold of cosmic voids to the artificial cold created by human ingenuity. Places where scientists have learned to manipulate matter with such precision that they can create temperatures colder than anywhere in the natural universe, colder even than the depths of intergalactic space, colder than should be possible according to the everyday logic of thermal physics. In laboratories scattered across our planet, patient researchers work with an almost monastic dedication to push the boundaries of cold, using techniques so sophisticated they seem to border on magic, so precise they require controlling individual atoms like a cosmic choreographer directing a dance of quantum particles. These are the coldest places in the known universe, not natural formations like the Boomerang Nebula, but human-created pockets of ultra-low temperature, where matter begins to behave in ways that challenge our most fundamental assumptions about how the physical world should operate. The pursuit of absolute zero has become one of science's most beautiful and persistent quests, not because achieving perfect coldness would have immediate practical applications, though many have emerged along the way, but because the journey toward that unreachable goal teaches us profound lessons about the nature of matter, energy, and the quantum mechanical foundations of reality itself. The aristocracy of coldness, helium's royal behavior. Our story begins with helium, that noble gas that makes balloons float and voices sound comical, but which reveals its true character only in the realm of extreme cold. Helium is aristocratic in its thermal behavior. It refuses to freeze into a solid under normal atmospheric pressure, no matter how cold you make it, maintaining its gaseous dignity down to the lowest temperatures before finally condensing into liquid form. Liquid helium, first achieved by Dutch physicist Heike Kamerlingh Onnes in 1908, exists at about 4.2 Kelvin, minus 269 degrees Celsius, already colder than anything found naturally in the universe. But helium has more surprises in store. When cooled further to 2.17 Kelvin, it undergoes one of the most remarkable phase transitions in all of physics, transforming from ordinary liquid helium, called helium I, into something that seems to violate the basic rules of fluid behavior. This transformation creates helium-2, a superfluid that flows without any viscosity whatsoever, a liquid that has forgotten how to experience friction. Pour superfluid helium into a container, and it will flow up the walls and over the rim, defying gravity like a liquid that has learned to ignore one of the fundamental forces of nature. It can flow through cracks so narrow that no ordinary liquid could pass, can create fountain effects that seem to mock the laws of fluid dynamics, and can carry heat with such efficiency that it approaches the theoretical limits of thermal conductivity. Watching superfluid helium in action is like witnessing matter that has remembered how to be purely quantum mechanical, liquid that has shed the classical constraints that govern our everyday experience of flowing substances. It's a preview of the strange behaviors that emerge when matter gets cold enough for quantum effects to dominate over thermal motion. The magic of magnetic cooling, teaching atoms to stand still. But even liquid helium at 2.17 Kelvin is merely the entry point to the realm of ultra-low temperatures. To go colder, scientists have developed techniques that sound more like incantations than physics: magnetic cooling, laser cooling, evaporative cooling, methods that manipulate the quantum mechanical properties of atoms with exquisite precision. Magnetic cooling, also called adiabatic demagnetization, works by exploiting the magnetic properties of atomic nuclei. Imagine atoms as tiny compass needles that can point in different directions. When you apply a strong magnetic field, these atomic compasses align themselves with the field, creating order from chaos. This alignment process actually releases heat, warming the sample slightly. But here's the beautiful part. If you remove the magnetic field while keeping the sample perfectly isolated from its surroundings, those atomic compasses become disordered again, and in doing so, they absorb thermal energy from their surroundings. It's like borrowing thermal energy from the atom's motion to pay for the magnetic disorder, leaving behind matter that's colder than before. Using techniques like this, scientists can reach temperatures of millikelvins, thousands of a degree above absolute zero. At these temperatures, atoms move so slowly that their velocities can be measured in millimeters per second, rather than the hundreds of meters per second typical of room temperature gases. It's like watching matter transition from the frenzied dance of thermal motion to the stately procession of a formal ceremony. Laser cooling, teaching light to stop atoms. Perhaps the most elegant technique for achieving ultra-low temperatures is laser cooling, a process so counterintuitive that it seems to violate our basic understanding of how light and matter should interact. Common sense suggests that shining light on something should heat it up. After all, this is how solar heating works, how microwave ovens warm food, how sunlight warms your skin on a summer day. But laser cooling uses the quantum mechanical properties of light to do exactly the opposite. By carefully tuning laser light to specific frequencies, scientists can create a kind of optical molasses that slows atoms down through their interactions with photons. The key insight is that atoms can absorb and emit photons in ways that, on average, remove energy from their motion rather than adding to it. Imagine an atom moving toward a laser beam. If the laser frequency is carefully chosen, the atom will preferentially absorb photons when it's moving toward the light source, due to the Doppler effect, and emit photons in random directions. Over many absorption and emission cycles, this process preferentially removes energy from the atom's motion in the direction of the laser beam, gradually slowing it down. By surrounding atoms with laser beams from multiple directions, creating what physicists poetically call an optical molasses, scientists can slow atoms to speeds of just a few centimeters per second, corresponding to temperatures of microkelvin, millionths of a degree above absolute zero. At these temperatures, atoms behave more like slow-moving clouds of quantum probability than the discrete particles of our everyday intuition. The quantum ballet, when individual atoms become visible. At these ultra-low temperatures, something magical happens. Individual atoms become visible, not to the naked eye, but to sophisticated detection systems that can track the position and motion of single particles. Atoms that were once lost in the thermal chaos of room temperature matter become distinct, trackable entities whose quantum mechanical behaviors can be observed and manipulated with unprecedented precision. Scientists can now create atom traps, combinations of laser light and magnetic fields that hold individual atoms suspended in space like quantum pearls on invisible strings. These trapped atoms can be cooled to nanokelvin temperatures, billionths of a degree above absolute zero, where they exist in a state of almost perfect stillness, their motion reduced to the minimum allowed by quantum mechanics itself. In this regime, atoms begin to exhibit behaviors that have no classical analogies. They can exist in multiple locations simultaneously, tunnel through barriers that should be impenetrable, and become entangled with each other in ways that seem to allow instantaneous communication across arbitrary distances. The familiar world of classical physics gives way to a quantum wonderland where the ordinary rules of reality seem suspended. Bose-Einstein condensates. When atoms forget their individual, push temperatures even lower, into the realm of billionths of a degree above absolute zero, and matter achieves something that Einstein predicted, but thought might never be observed: Bose-Einstein condensation. At these incredible temperatures, achieved only in the most sophisticated laboratories using combinations of laser cooling, magnetic trapping, and evaporative cooling, individual atoms begin to lose their separate identities. In a Bose-Einstein condensate, thousands or millions of atoms settle into the same quantum mechanical state, becoming effectively a single, macroscopic quantum object. It's as if the atoms have forgotten that they're supposed to be individual particles and have merged into a collective quantum entity that behaves more like a wave than a collection of discrete objects. This isn't just a theoretical curiosity. Bose-Einstein condensates exhibit properties that seem to defy common sense. They can flow without friction like superfluids, but they're made of matter so tenuous that they're barely there at all. They can interfere with themselves like waves of light, creating patterns that reveal the wave-like nature of matter itself. They can be shaped and manipulated with magnetic fields and laser light, allowing scientists to create quantum matter in almost any configuration they can imagine. The creation of the first Bose-Einstein condensate in 1995 was like achieving a new state of matter, a form of substance that exists nowhere naturally in the universe, but can be coaxed into existence by human technology and patience. It's matter that has learned to be purely quantum mechanical, substance that exists in a state of collective quantum coherence that bridges the microscopic world of individual atoms and the macroscopic world of everyday objects. The quantum refrigerator, cooling with quantum mechanics. The techniques for achieving these ultra-low temperatures have become so sophisticated that they now involve quantum mechanics, not just in their outcomes but in their methods. Quantum refrigeration uses the strange properties of quantum entanglement and quantum measurement to extract heat from systems in ways that classical thermodynamics would consider impossible. One such technique, called algorithmic cooling, uses quantum computers not to perform calculations, but to serve as incredibly efficient refrigerators, using quantum algorithms to pump heat out of quantum systems and achieve temperatures that approach absolute zero from below, a statement that sounds paradoxical but makes perfect sense in the context of quantum thermodynamics. These quantum cooling techniques have revealed that the approach to absolute zero is not just a matter of removing thermal energy, but of entering a regime where the distinction between energy and information begins to blur, where cooling becomes a process of organizing quantum information rather than simply removing heat. The laboratory as cosmic theater, recreating the universe's extremes. Perhaps the most remarkable aspect of these ultra-low temperature laboratories is that they allow scientists to recreate and study conditions that exist nowhere else in the universe. The coldest temperatures ever achieved on Earth are now colder than the depths of intergalactic space, colder than the Boomerang Nebula, colder than any natural environment we know of. In these laboratories, scientists can study quantum phase transitions that occurred in the early universe, simulate the behavior of matter under conditions that existed microseconds after the Big Bang, and explore quantum many-body physics that governs everything from superconductivity to the exotic matter that might exist in the cores of neutron stars. The laboratory becomes a kind of cosmic theater where the most extreme conditions in the universe can be reproduced and studied at leisure, where the rarest states of matter become accessible to human investigation, where the boundary between natural and artificial, between discovered and created, begins to blur in productive and beautiful ways. The practical magic of extreme cold, technologies born from curiosity, these explorations of ultra-low temperatures, driven initially by pure scientific curiosity about the limits of coldness and the behavior of matter under extreme conditions, have yielded practical applications that now touch daily life in ways both visible and invisible. Magnetic resonance imaging. MRI machines rely on superconducting magnets, cooled by liquid helium to create the strong, stable magnetic fields necessary for medical imaging. GPS satellites depend on atomic clocks that use laser-cooled atoms to maintain their precision. Quantum computers, still in their infancy, but promising revolutionary advances in computing power, rely on ultra-low temperature environments to maintain the quantum coherence necessary for quantum computation. The pursuit of absolute zero has become not just a scientific quest but a technological driver, pushing the development of new materials, new measurement techniques, new ways of controlling and manipulating matter at the most fundamental levels. The coldest places on Earth have become some of the most technologically sophisticated environments humans have ever created. The philosophy of approaching perfection. Lessons from the asymptotic journey. There's something deeply philosophical about the quest for absolute zero, something that speaks to the human relationship with perfection and limits. According to the third law of thermodynamics, absolute zero cannot be reached in a finite number of steps. It's an asymptotic goal, approachable but never quite achievable, like trying to reach the horizon by walking toward it. This mathematical impossibility hasn't deterred scientists, if anything. It has inspired them to push closer and closer to this unreachable goal, achieving temperatures that differ from absolute zero by smaller and smaller fractions. Each advance in cooling technology brings us closer to perfection while teaching us more about the quantum mechanical nature of reality. The journey toward absolute zero has become a metaphor for the scientific enterprise itself. The pursuit of perfect knowledge, perfect understanding, perfect control over natural phenomena, with the recognition that these goals may be asymptotic, always approachable, never quite achievable, but invaluable in the approaching. The warmth of human achievement, finding heat in cold. As you rest tonight in your naturally warm corner of the universe, maintained at a comfortable temperature by the thermal processes of your living body, there's something beautiful about knowing that humans have learned to create conditions colder than anything nature produces, colder than the space between galaxies, colder than the hearts of dying stars. These ultra-cold laboratories represent one of humanity's most remarkable achievements: the ability to create artificial environments that extend the range of natural conditions, to push matter into regimes where its behavior becomes purely quantum mechanical, to touch the limits of what temperature means in a universe governed by quantum mechanics and thermodynamics. The scientists working in these laboratories are like thermal artists, using sophisticated tools to sculpt matter at temperatures so low they approach the theoretical limits of coldness itself. They work in a realm where classical physics gives way to quantum strangeness, where matter forgets how to behave according to everyday logic, where the familiar rules of thermal behavior are replaced by the alien logic of quantum mechanics. In creating these impossibly cold environments, humanity has not just extended the range of achievable temperatures, we've created new states of matter, new ways for atoms to exist and interact, new windows into the quantum mechanical foundations of reality itself. We've learned to make matter so still that its wave-like properties become visible, so cold that individual atoms become as manageable as visible objects, so quantum that the boundary between matter and energy begins to blur. These achievements represent a kind of thermal poetry, a demonstration that human curiosity and ingenuity can push the boundaries of what's possible, can create conditions that extend the natural world into realms of artificial perfection. In the coldest places humans have ever created, we find not just the absence of heat, but the presence of wonder, the manifestation of our species' remarkable ability to understand and manipulate the fundamental properties of matter itself. Sleep well tonight, knowing that somewhere in laboratories around the world, dedicated scientists are maintaining temperatures colder than the space between stars, creating conditions where matter reveals its most exotic behaviors, pushing ever closer to the unreachable goal of absolute zero, while discovering along the way new truths about the quantum mechanical foundations of the universe itself. The warmth of infinite perspective. And so, dear dreamer, our gentle journey through the universe's coldest places draws to a close, like a symphony ending not with dramatic crescendo, but with the softest possible whisper, fading into silence that contains within it all the notes that came before. We have travelled together from the familiar cold of winter mornings to the exotic cold of quantum laboratories, from the natural refrigerator of the Boomerang Nebula to the artificial perfection of Bose-Einstein condensates. We've explored temperatures so low they make the space between galaxies seem balmy, and discovered that in the pursuit of perfect coldness, humanity has learned to create conditions more extreme than anything nature produces in its vast, patient laboratories. What emerges from this thermal odyssey is not just knowledge about temperature and thermodynamics, but a profound sense of perspective about our place in a universe that spans an almost inconceivable range of conditions, from the nuclear fires of stellar cores to the quantum stillness of ultra-cold atoms, from the ancient warmth of the cosmic microwave background to the artificial cold of human ingenuity. Temperature becomes a window into the full scope of physical reality. Tonight, as you settle into sleep in your own perfectly temperate corner of existence, you carry with you the knowledge that you exist in a narrow thermal band that represents just a tiny fraction of the universe's full temperature range. Yet this knowledge doesn't diminish your significance. Instead, it illuminates the remarkable improbability and preciousness of the conditions that allow complex chemistry, biological processes, and conscious thought to flourish. You are warm, not by accident, but by the coordinated action of countless physical processes: the nuclear fusion in our sun that provides energy, the greenhouse effect of our atmosphere that moderates temperature, the biochemical reactions in your cells that maintain your body's thermal equilibrium, the quantum mechanical behavior of molecules that allows life's chemistry to proceed at just the right pace. In contemplating the universe's coldest places, we discover something beautiful about warmth itself, that it's not just the absence of cold, but the presence of energy, motion, possibility, life. The warmth of your body as you rest tonight is a kind of miracle, a localized resistance to the universe's tendency toward thermal equilibrium, a temporary victory of order and complexity over the patient pull toward maximum entropy. The cosmic perspective we've gained tonight suggests that warmth and cold are partners in the universe's grand thermal dance, each defining the other, each necessary for the full expression of physical reality. Without cold, there would be no temperature gradients to drive weather systems, ocean currents, or the flow of energy that powers the complex processes of life. Without warmth, there would be no energy to animate matter, no chemistry to create complexity, no conditions suitable for the emergence of consciousness. As you drift towards sleep, let your breathing slow to match the patient rhythm of the universe itself, the expansion of space, the cooling of the cosmic microwave background, the gradual approach toward maximum entropy that will characterize the far future of the cosmos. Yet even this ultimate thermal death, billions of years in the future, carries within it a kind of beauty, the universe's final achievement of perfect thermal equilibrium, a state of cosmic peace where all temperature gradients have been erased and all energy has been shared equally across all of space. But that future is unimaginably distant, and the present moment is warm with possibility. The universe still has billions of years of thermal disequilibrium ahead of it, billions of years of stars burning and planets forming, and the complex chemistry of life unfolding in countless corners of the cosmos. The coldest places we've explored tonight exist against this backdrop of cosmic abundance, temporary pockets of extreme conditions in a universe still rich with energy and possibility. Your consciousness, contemplating these thermal extremes from the comfortable warmth of your own existence, represents one of the universe's most remarkable achievements, matter that has become sufficiently complex and organized to reflect upon itself, to measure and understand its own thermal properties, to create artificial conditions that extend the range of natural possibilities. In learning to touch absolute zero, humanity has not just mastered the physics of extreme cold. We've demonstrated the universe's capacity for self-understanding through the emergence of conscious beings capable of exploring its furthest extremes. The coldest temperatures ever achieved exist not in some distant cosmic location, but here on Earth, created by conscious minds curious about the limits of temperature itself. This is perhaps the most beautiful lesson of our thermal journey, that the universe has evolved conscious observers, capable of exploring conditions more extreme than anything it produces naturally, conscious beings who can create artificial perfection in the pursuit of understanding the natural world. The coldest places in the known universe exist in human laboratories, created by human curiosity, measured by human instruments, understood by human minds. Rest now in the warmth of this knowledge, secure in your place in the universe's thermal landscape, connected by invisible threads of physics to everything from the hottest stellar cores to the coldest quantum gases. The cosmic microwave background radiation passes through your body at this very moment, connecting you to the universe's origin story. The same quantum mechanical principles that govern ultra-cold atoms also govern the chemistry of your living cells. You are not separate from the thermal extremes we've explored. You are part of them, connected to them, defined in relation to them. Your warmth exists in dialogue with cosmic cold. Your consciousness emerged from the same physical processes that govern temperature and entropy throughout the universe. Sleep well, cosmic citizen, dreamer of temperatures absolute, contemplator of quantum mechanical perfection. Tomorrow you will wake in the same narrow thermal range that has nurtured consciousness since its first emergence on Earth. But tonight you carry with you the knowledge of the full scope of thermal possibility, the complete spectrum of temperature that defines the physical universe, from its hottest fires to its coldest silences. In the gentle transition from wakefulness to sleep, you recapitulate in miniature the universe's own journey from the hot chaos of the Big Bang to the patient, cooling expansion that characterizes cosmic evolution. Your cooling body temperature, as you relax, mirrors the cooling of the cosmos itself. Your slowing thoughts echo the slowing dance of atoms as they approach absolute stillness. Dream of temperatures unimaginable, of atoms so still they forget to move, of consciousness warm enough to contemplate its own place in the cosmic thermal spectrum. Dream of the Boomerang Nebula's impossible cold, of liquid helium flowing upward in defiance of gravity, of laser light teaching atoms to stand perfectly still. And when you wake, refreshed and warm, with the energy of biological processes that have maintained their thermal equilibrium through the night, you will know yourself to be part of something vast and beautiful. A universe that spans from perfect cold to stellar fire, from quantum stillness to nuclear fusion, from the absolute zero of theoretical physics to the warmth of conscious life contemplating its own thermal nature. The coldest places in the universe have taught us the deepest appreciation for warmth, for energy, for the remarkable conditions that allow complexity and consciousness to flourish in a cosmos where most of space and time is characterized by profound cold and patient emptiness. Good night, warm dreamer. May your sleep be as peaceful as the spaces between stars, as gentle as atoms approaching absolute zero, as profound as the cosmic background radiation that connects all corners of existence to their shared origin, in the hot birth of everything that ever was or ever will be. The paradox of stellar birth. Yet in this seeming emptiness, something remarkable occurs. The coldest regions of interstellar space are also the birthplaces of the hottest objects in the universe. These stellar nurseries are called molecular clouds, vast shadowy regions where temperatures can plunge as low as 10 Kelvin and where the next generation of suns quietly gestates. These clouds are composed primarily of molecular hydrogen, with traces of helium, carbon monoxide, ammonia, and other simple molecules. Scattered throughout are tiny dust particles, grains of carbon and silicon, coated with ices that play a crucial role in keeping these regions cold by blocking the warming ultraviolet radiation from distant stars. Cold, it turns out, is essential for star formation. In warmer gas, atoms move too quickly and collide too violently to stick together. But in these frigid molecular clouds, atoms move with gentle deliberation, allowing them to bond into stable molecules and eventually to succumb to the patient pull of gravity. Chemistry in the deep freeze. Within these dark, cold regions, a surprisingly rich chemistry unfolds. Despite temperatures that would make Antarctic winters seem balmy, atoms slowly find each other and form bonds, not just simple hydrogen pairs, but complex molecules like formaldehyde, methanol, and even precursors to amino acids, the building blocks of life itself. This chemistry proceeds at a pace that makes glacials seem hurried. Atoms drift through space for thousands of years before encountering potential partners. When they do meet, it's with the gentleness of snowflakes settling, allowing bonds to form that would be instantly broken in warmer environments. The dust particles scattered through these clouds serve as more than just cosmic sunblock. They act as catalysts and meeting places where atoms can gather, stick, and react. Ice forms on their surfaces, creating tiny laboratories where ultraviolet photons from distant stars can drive reactions that produce increasingly complex compounds. In laboratory simulations mimicking these conditions, scientists have created amino acids from these cosmic ice mixtures, suggesting that space itself may be quietly rehearsing the chemistry of life in its coldest corners. The invisible architecture. We can't see these molecular clouds in visible light because they absorb and scatter it so effectively. Instead, astronomers detect them using radio telescopes and infrared instruments, where they appear as dark patches against the star field, like smudges on the cosmic window, hiding the light beyond. Some of these clouds are enormous, stretching for hundreds of light years and persisting for millions of years. During this vast span of time, the cold isn't a temporary weather pattern, it's a permanent condition that allows the slow work of cosmic construction to proceed undisturbed. One of the most famous examples lies within the constellation Orion, in the molecular cloud complex that serves as a stellar nursery for our local region of the galaxy. Here, dense cores of gas and dust wait patiently for gravity to tip the balance, beginning the slow collapse that will eventually ignite new stars. The colder depths. In the densest hearts of these molecular clouds, temperatures drop even lower. Here, even carbon monoxide, a gas that remains airborne on Earth down to -200 degrees Celsius, freezes out onto dust grains, forming icy mantles that become cosmic chemistry sets. Under just the right conditions, these ice-coated particles become the laboratories where complex organic molecules are born from the simplest ingredients: hydrogen, carbon, oxygen, and time. Between the galaxies themselves, in the truly intergalactic voids, conditions become even more extreme. Here, temperatures stay locked near the cosmic microwave background limit of 2.7 Kelvin, but the density drops to nearly absolute zero. These regions are so empty that molecular clouds cannot form. There simply isn't enough material for gravity to gather into anything substantive. Instead, individual atoms drift through space for billions of years, separated by distances that dwarf solar systems. The fertile emptiness. Yet this seeming sterility serves a purpose. The emptiness provides the contrast that makes stellar light meaningful, the silence that allows cosmic music to be heard, the cold that gives warmth its definition. Without these vast, frigid spaces, there would be no islands of heat where life could flourish, no dramatic temperature gradients to drive the evolution of complexity. In these cold depths, the universe practices patience on a scale that dwarfs human comprehension. Atoms drift for millennia before meeting. Molecules form over geological timescales. Stars gestate for millions of years in the dark, cold embrace of their maternal clouds, before finally igniting into brilliance. The hopeful void. There's something profoundly hopeful about these coldest regions of space. They're not empty wastelands, but nurseries, places where the future is quietly under construction. Every star that will ever burn, every planet that will ever form, every possibility for life that will ever emerge, begins its story in these frigid depths. As you rest in the warmth of your earthly haven tonight, remember that somewhere in the cold spaces between the stars, the next chapter of the cosmic story is being written. Atoms are finding each other across impossible distances. Molecules are forming that have never existed before. And somewhere in a dark, cold cloud, gravity is taking its first tentative steps toward creating a new sun. The coldest places in the universe, it turns out, are also its most hopeful, the quiet workshops where everything begins, where possibility condenses out of emptiness, and where the future grows slowly but inevitably, 1 degree above absolute zero. Earthbound ice laboratories of extreme cold. While the universe's natural refrigerators float serenely through space, some of the most remarkably cold places in existence are created right here on Earth, tucked away inside laboratories where human ingenuity has learned to whisper atoms into near-perfect stillness. These are places where the ordinary rules of matter begin to bend, where quantum mechanics steps out of the shadows, and where temperatures so low are achieved that they redefine our understanding of what's possible. Getting close to absolute zero, that theoretical point of perfect atomic stillness at 0 Kelvin, or minus 273.15 degrees Celsius, requires more than simply building a better refrigerator. At these extreme temperatures, conventional thinking breaks down entirely. Atoms move so slowly they begin to behave less like tiny particles and more like quantum waves, entering a realm where individual identity blurs into collective behavior. The gentle art of laser cooling, whispering atoms to sleep. Picture a single atom, no bigger than a whisper, dancing through space with the restless energy of a child who's had too much sugar. Now imagine we could sing it a lullaby, not with our voices, but with carefully tuned beams of light. This is the mesmerizing art of laser cooling, where scientists have learned to use photons like gentle hands, slowing atoms until they barely move at all. When most people think of lasers, they envision searing heat, cutting through steel, cauterizing wounds, or that mischievous red dot that sends house cats into delightful frenzies. But here's where physics becomes poetry. Properly tuned lasers can actually cradle atoms into stillness with breathtaking precision. Imagine our restless atom zipping through space, its quantum heart beating with kinetic energy. Now picture a laser beam approaching from the opposite direction, its frequency tuned to exactly the right note, the atom's favorite wavelength, if you will. When the atom absorbs a photon from this opposing beam, it receives a tiny nudge backward, like catching a feather while running through a gentle breeze. But here's where the magic deepens. Scientists surround the atom with a constellation of laser beams, each one perfectly choreographed to slow motion in every direction. It's like being embraced by 6 gentle giants, each one whispering, "Slow down, little one, rest now." The atom begins to move more and more slowly, its frantic dance settling into a peaceful waltz, then a gentle sway, then finally stillness. At these impossibly low temperatures, we're talking about fractions of degrees above absolute zero, atoms begin to behave like quantum dreamers. They lose their individual identities and merge into what physicists call a Bose-Einstein condensate, a state of matter so ethereal it seems more like a living cloud of possibility than ordinary matter. Imagine thousands of snowflakes falling so slowly and peacefully that they forget they're separate and become one unified, glistening blanket of quantum snow. The mathematics behind this process are as elegant as they are complex. Each photon carries not just energy but momentum, about 10 circumflex 27 kilogram meters per second. When an atom absorbs millions of these photons over time, each tiny push accumulates like gentle raindrops eventually filling a pond. The Doppler effect plays a crucial role too. As the atom slows down, it becomes less likely to absorb photons from the same direction, creating a natural braking system that prevents the process from overshooting. Cosmic heaters, the steady heartbeat of deep space. In the profound darkness between stars, where no earthly campfire could ever burn, human ingenuity has created its own form of artificial warmth. Enter the radioisotope thermoelectric generator, the RTG, a device so elegantly simple, yet so profoundly important, that it deserves to be called the beating heart of deep space exploration. An RTG is in essence a nuclear lullaby. Deep within its protective shell, plutonium-238 atoms are slowly, peacefully decaying, not in the violent way of nuclear weapons, but in a gentle, predictable rhythm that has remained constant for billions of years. Each decay event releases a tiny puff of heat, like a microscopic ember glowing in the cosmic dark. This heat flows through thermoelectric couples, clever devices that convert temperature differences directly into electricity, as reliably as a water wheel converts flowing water into mechanical motion. There's something deeply moving about this process. No moving parts, no fuel tanks to refill, no solar panels to clean, just the inexorable pulse of atomic decay, converting matter into energy at nature's own steady pace. It's as if we've learned to harness the universe's own metabolic rate, the slow breathing of matter itself. Consider the Voyager spacecraft, those twin ambassadors launched in 1977 when disco was still king and the internet was barely a gleam in a researcher's eye. More than 47 years later, they continue to drift through interstellar space, powered by their faithful RTGs. By now, they're so far from the sun that our star appears as nothing more than a bright point of light, offering less warmth than a flashlight beam at midnight. Solar panels would be utterly useless out there, the equivalent of trying to charge your phone with candlelight. But their nuclear hearts keep beating, maintaining a core temperature warm enough to keep their instruments functional and their radio transmitters strong enough to whisper their discoveries across the vast cosmic distances. It takes over 22 hours for their signals to reach Earth now, a radio conversation where each exchange requires nearly 2 full days. The physics of RTG operation involves the Seebeck effect, discovered by Thomas Johann Seebeck in 1821. When two different metals are joined and their junction is heated, a voltage develops across the connection. In space-grade RTGs, this effect is enhanced using semiconductor materials like lead telluride, which can maintain efficiency even after decades of radiation exposure and thermal cycling. The James Webb Space Telescope presents us with a fascinating paradox, a machine that doesn't want to stay warm but desperately needs to stay cold. Webb's golden mirrors and sophisticated instruments are designed to detect the faintest infrared light from the most distant galaxies, light that has been traveling toward us since the universe was young and small. But infrared light is essentially heat radiation, and any warmth from the telescope itself would create a blinding glare, like trying to see distant stars while holding a torch next to your eyes. To achieve this cosmic chill, Webb employs a sunshield the size of a tennis court, 5 gossamer-thin layers that block light and heat from the sun, earth and moon with the dedication of a devoted guardian. Each layer is separated by a carefully calculated gap, allowing heat to radiate harmlessly into space while protecting the instruments behind it. The result is a temperature drop of nearly 600 degrees Fahrenheit from the hot side to the cold side of the shield. On the cold side, where the scientific instruments rest, temperatures plummet to around 40 Kelvin. That's minus 388 degrees Fahrenheit, cold enough to freeze atmospheric gases solid. One of Webb's instruments, the mid-infrared instrument, MIRI, is actively cooled even further using a specialized cryocooler that brings its detector down to just 7 Kelvin. At this temperature, the individual atoms in the detector array barely vibrate, creating an almost perfect quantum silence that allows it to detect the faintest whispers of ancient starlight. The dream of cryosleep. When science fiction meets frozen reality, there's something undeniably enchanting about the idea of cryogenic sleep, that gentle drift into a crystalline dream state where time itself seems to pause. It's appeared in countless stories, from the crew of the Nostromo in Alien to the colonists in Passengers, always promising the same thing: close your eyes in 1 century, open them in another with nothing lost but time itself. But here in our waking world, the reality is both more complex and more fascinating than fiction suggests. Nature herself has already shown us the possibilities. Arctic ground squirrels that can survive with their blood temperature below freezing, their hearts stopped for months at a time, wood frogs that become living ice sculptures each winter, Their cells protected by natural antifreeze proteins that prevent deadly ice crystal formation. The human body, unfortunately, didn't evolve with such convenient features. When our tissues freeze, water inside our cells expands into sharp-edged ice crystals that puncture cell membranes like microscopic daggers. The result isn't peaceful slumber, it's catastrophic cellular destruction, death by a billion tiny cuts. To circumvent this harsh reality, scientists have developed the elegant process of cryopreservation, a technique that involves replacing the water in cells with special antifreeze compounds called cryoprotectants. These molecular guardians, substances like dimethyl sulfoxide and ethylene glycol, slip between water molecules and prevent them from forming their characteristic crystalline lattices. Instead of ice, the cellular contents become vitrified, transformed into a glass-like state that preserves structure without the destructive expansion of freezing. This process already works beautifully for small biological structures. Sperm, eggs, embryos, and thin tissue samples can be frozen to -196 degrees Celsius, the temperature of liquid nitrogen, and revived years later with remarkable success rates. Corneas for transplants, skin grafts for burn victims, and even whole ovaries have been preserved and successfully transplanted using these techniques. But scaling up to an entire human body presents challenges that make climbing Everest look like a gentle stroll. The human brain alone contains approximately 86 billion neurons, each connected to thousands of others in a network more complex than the entire internet. Getting cryoprotectants to penetrate evenly throughout this vast neural web, while ensuring uniform cooling and warming rates across different tissue types, remains one of the most daunting problems in modern biology. The mathematics of heat transfer become particularly cruel at these scales. Cooling rates must be fast enough to prevent ice formation, but not so fast that thermal stress fractures tissues. Warming must be even more carefully controlled. Too slow, and ice crystals form during the thaw. Too fast, and thermal expansion causes mechanical damage. It's like trying to defrost a Thanksgiving turkey while maintaining the structural integrity of every single cell. Recent advances in vitrification have shown promise. Scientists have successfully preserved and revived small organs like kidneys and livers using these techniques, though the success rates remain far from perfect. The process requires precise timing, enormous coordination and equipment that makes a modern hospital look simple by comparison. Hidden oceans in frozen worlds where ice becomes life's guardian. Some of the most thrilling discoveries in recent decades have come from places we once dismissed as frozen wastelands. The icy moons of Jupiter and Saturn that orbit in the cold outer reaches of our solar system, where sunlight arrives weak and distant, barely strong enough to power a solar calculator. Europa, one of Jupiter's largest moons, appears at first glance like a billiard ball dipped in cracked ice. Its surface temperature hovers around -160 degrees Celsius, cold enough to make Antarctic winters feel tropical. But this gleaming shell of ice may be hiding one of the most extraordinary secrets in our solar system, a vast liquid ocean containing more water than all Earth's oceans combined. How can liquid water exist in such a frozen realm? The answer lies in one of nature's most elegant heating systems, tidal flexing. As Europa orbits Jupiter, the massive planet's gravity stretches and squeezes the moon like a cosmic stress ball. This constant kneading generates internal friction, converting gravitational energy into heat, enough heat to keep a global ocean liquid beneath kilometers of protective ice. Picture this hidden sea, darker than the deepest Earth ocean, possibly saltier than the Dead Sea, stirred by currents powered, not by wind or sunlight, but by the gravitational dance of celestial mechanics. If hydrothermal vents exist on Europa's ocean floor, and many scientists believe they do, this alien sea might host entire ecosystems powered by chemosynthesis, life that feeds on chemical energy rather than solar energy. Enceladus, Saturn's tiny ice moon, is even more dramatic in its revelations. Barely 500 kilometers across, smaller than the state of Texas, it erupts with geysers of water vapor and ice particles that spray hundreds of kilometers into space. These aren't gentle hot springs. They're powerful jets shooting through cracks in the south polar region at speeds of up to 2,000 kilometers per hour. When the Cassini spacecraft flew through these plumes, it discovered something that sent ripples of excitement through the scientific community: organic molecules. Complex carbon-based compounds, the building blocks of life as we know it, were being ejected from Enceladus's hidden ocean and sprayed into space like an advertisement for potential biology. The physics behind these geysers involves a fascinating interplay of tidal heating, subsurface ocean dynamics, and thermodynamics. As tidal forces heat Enceladus's interior, the subsurface ocean experiences convection currents. When these warm currents encounter the ice shell from below, they create pockets of liquid that eventually find their way to the surface through the famous tiger stripe, fractures near the South Pole. Even distant Pluto, demoted from planet to dwarf planet, but promoted in our understanding of its complexity, has surprised us with signs of activity. When New Horizons flew past in 2015, it revealed a world with nitrogen glaciers, methane dunes, and possible subsurface oceans. The famous heart-shaped feature, Tumbor Regio, shows signs of recent geological activity on a world that receives only 0.06% as much sunlight as Earth. The implications are staggering. If life can exist in these hidden oceans, then the habitable zone around stars, that narrow band where liquid water can exist on a planet's surface, may be far too restrictive a definition. Icy moons with subsurface oceans could be common throughout the galaxy, each one a potential cradle for biology we've never imagined. The mystery of cold dark matter, the universe's invisible architecture. In the cosmic library of mysterious phenomena, few topics are as simultaneously fundamental and puzzling as dark matter. Despite its name suggesting something frozen and shadowy, dark matter isn't dark because of temperature. It's dark because it doesn't interact with light at all. It neither emits, absorbs, nor reflects electromagnetic radiation of any kind. It's transparent to photons, invisible to telescopes, and yet it shapes the very architecture of the universe. The cold in cold dark matter refers not to temperature but to velocity, specifically how fast these mysterious particles were moving in the early universe when the first structures began to form. Cold dark matter particles moved slowly compared to the speed of light, allowing them to clump together under their own gravity and form the scaffolding upon which galaxies, galaxy clusters, and the vast cosmic web were built. Imagine the early universe as a vast, nearly smooth soup of matter and energy, tiny ripples in density, quantum fluctuations from the Big Bang itself provided the seeds for structure formation. In regions where dark matter particles moved slowly, hence cold, these ripples could grow. Gravity pulled more matter into these slight overdensities, which attracted even more matter in a beautiful positive feedback loop that eventually created the cosmic web we observe today. If dark matter had been hot, moving at nearly the speed of light in the early universe, these particles would have smoothed out the small-scale structure, making it difficult for galaxies to form. The universe would have remained frustratingly homogeneous, like cream that's been stirred so thoroughly it can never separate again. Current models suggest that cold dark matter makes up about 27% of the universe's total mass energy content. That means that for every kilogram of ordinary matter, protons, neutrons, electrons, all the stuff that makes up stars, planets, and people, there are about 5.4 kilograms of dark matter. Everything you've ever seen, touched, or thought about represents less than 5% of the universe. The rest is dark matter, dark energy, and mystery. The evidence for dark matter comes from its gravitational effects. Galaxies rotate too fast for the visible matter alone to hold them together. The stars in the outer regions should be flying off into space like mud from a spinning bicycle tire. Galaxy clusters move in ways that suggest far more mass than we can account for with visible matter. Gravitational lensing, the bending of light by massive objects, shows us the presence of matter we cannot see. Computer simulations that include cold, dark matter produce a universe that looks remarkably like our own, a cosmic web of filaments and voids, galaxy clusters connected by dark bridges of matter, and empty regions that span hundreds of millions of light years. It's as if the universe is a vast neural network, with dark matter forming the invisible connections between nodes of visible matter. Despite decades of searching, we haven't directly detected a single dark matter particle. Deep underground laboratories shield delicate detectors from cosmic rays, waiting for the telltale sign of a dark matter particle colliding with a normal atom. So far, these experiments have been met with profound silence. The particles, if they exist, are even more elusive than we imagined. The heat death of the universe, a gentle fade to cosmic black. If the universe were to write its autobiography, the final chapter would be titled something like The Long Goodbye, or perhaps Entropy's Victory. This isn't the dramatic ending that science fiction often imagines. No exploding suns, no cosmic catastrophes, no alien invasions. Instead, it's a story of gradual cooling, of energy slowly spreading itself thinner and thinner until there's nothing left to power change. This theoretical finale is called the heat death of the universe, though it has little to do with heat as we experience it. It's actually the ultimate cold, a state where the universe reaches maximum entropy and minimum useful energy, like a cup of coffee that has finally reached room temperature and can cool no further. To understand this cosmic endgame, we need to appreciate the second law of thermodynamics, one of the most fundamental and inescapable rules in physics. It states that in any closed system, entropy, roughly speaking, disorder, always increases over time. Perfume spreads throughout a room. Energy flows from concentrated forms to dispersed forms, and this process is irreversible on cosmic scales. Right now, the universe is delightfully out of equilibrium. Stars burn nuclear fuel and shine brightly. Galaxies collide and trigger new star formation. Black holes feast on nearby matter and shoot jets of particles across millions of light years. There are temperature differences, energy gradients, and fascinating imbalances that drive all the cosmic activity we observe. But this won't last forever. Fast forward a few trillion years, a time span that makes the current age of the universe look like a brief afternoon nap, and the stellar nurseries will have closed. The most massive stars will have burned out quickly in spectacular supernova. Medium-sized stars like our Sun will have swollen into red giants, then collapsed into white dwarfs. The smallest red dwarf stars, those cosmic misers that burn their fuel so slowly they could theoretically shine for 1 trillion years, will finally exhaust their nuclear reserves. What remains will be a universe of stellar corpses, white dwarfs, neutron stars and black holes drifting through an ever-expanding space that grows colder and darker with each passing eon. The white dwarfs, those hot, dense cores of former stars, will slowly radiate away their stored heat over quadrillions of years, cooling from brilliant white to red to infrared to nothing. Black dwarfs, they'll be called cold, dark spheres of carbon and oxygen, invisible monuments to stars that once burned bright. But even black holes, once thought to be eternal vacuum cleaners that could never stop growing, have a finite lifespan. Stephen Hawking's brilliant insight showed us that black holes slowly evaporate through quantum effects, losing mass by emitting what's now called Hawking radiation. This process is extraordinarily slow. A black hole with the mass of our Sun would take 10 circumflex, 67 years to completely evaporate, a number so large it strains the imagination. The largest black holes, those supermassive giants that anchor galaxy centers, will persist much longer, perhaps 10 circumflex 100 years or more. But eventually, even they will fade into quantum mist, leaving behind only a sparse soup of elementary particles and photons in a universe that has expanded to unimaginable size and cooled to within a whisper of absolute zero. At this point, so new structures can form. There's no available energy to drive chemical reactions, no temperature gradients to power engines, no imbalances to create complexity. The universe will have reached thermodynamic equilibrium, maximum entropy, minimum useful energy, perfect uniformity. It's not death in any violent sense. It's more like the universe finally relaxing after 10 circumflex 100 years of ceaseless activity. The coldest experiments on Earth, approaching absolute stillness. While the universe contains regions of profound cold, some of the coldest temperatures ever achieved exist not in the depths of space, but in carefully controlled laboratories here on Earth. These experiments represent one of humanity's most precise and ambitious endeavors, the quest to approach absolute zero, that theoretical temperature where molecular motion essentially stops. At the Massachusetts Institute of Technology, researchers have created temperatures as low as 500 picokelvin, that's 500 trillionths of a degree above absolute zero. To put this in perspective, this temperature is colder than anywhere else known in the universe, including the cosmic microwave background radiation that permeates all of space. The journey to such extreme cold begins with laser cooling, the elegant process we explored earlier, where carefully tuned light beams slow atoms to a crawl, but laser cooling alone can only take you so far, typically down to about a millikelvin. To go colder, scientists employ evaporative cooling, a technique borrowed from nature's own cooling system, perspiration. Just as your skin cools when the most energetic water molecules evaporate as sweat, leaving the cooler molecules behind, scientists can selectively remove the most energetic atoms from their trapped sample. What remains is a cloud of atoms with lower average kinetic energy, and therefore lower temperature. It's like skimming the foam off hot chocolate, except the foam consists of the fastest moving atoms in a magnetic trap. At these impossibly low temperatures, quantum mechanics takes over completely. Individual atoms lose their classical identities and begin to behave as quantum waves. When cooled sufficiently, thousands or millions of atoms can occupy the same quantum state, creating what's called a Bose-Einstein condensate, a new state of matter that Albert Einstein and Satyendra Nath Bose predicted in the 1920s, but which wasn't observed until 1995. In a Bose-Einstein condensate, atoms don't just crowd together physically, they become quantum mechanically identical, sharing the same wave function like a vast choir singing in perfect unison. The condensate behaves less like a collection of particles and more like a single macroscopic quantum object, matter that acts like a wave on scales visible to the naked eye. NASA's Cold Atom Laboratory, operating aboard the International Space Station, takes these experiments to a new level by eliminating gravity's influence. On Earth, gravity eventually pulls the ultra-cold atoms downward, limiting observation time to fractions of a second. In microgravity, these quantum gases can float freely for much longer periods, allowing scientists to study their behavior in unprecedented detail. The physics involved in creating these temperatures involves a delicate interplay of electromagnetic fields, precisely controlled laser frequencies, and quantum mechanics. Magnetic traps use the fact that atoms with magnetic moments experience forces in non-uniform magnetic fields. By creating a magnetic bowl in space, scientists can confine atoms while minimizing their contact with warm surfaces. Optical lattices, standing waves of laser light, can create egg crate-like patterns of potential energy, trapping atoms at the intersections where the light intensity is either maximum or minimum. These optical crystals allow researchers to study quantum many-body physics, simulating the behavior of electrons in solid-state materials, but with exquisite control over every parameter. At CERN, the European Organization for Nuclear Research, scientists use extreme cold for a different purpose: trapping antimatter. The antiproton decelerator creates and stores antihydrogen atoms at temperatures below 1 Kelvin, cold enough to prevent these precious antiatoms from colliding with normal matter and annihilating. The goal is to perform precision measurements of antimatter's properties, potentially revealing why our universe is dominated by matter rather than equal amounts of matter and antimatter. These ultra-cold experiments aren't just scientific curiosities, they're laying the groundwork for quantum computers, ultra-precise atomic clocks, and sensors so sensitive they can detect gravitational waves or measure the acceleration due to gravity with unprecedented accuracy. By removing thermal noise, the random jittering of atoms due to temperature, these experiments create quantum systems of extraordinary purity and control. A universe without warmth, the poetry of perfect cold. Imagine, if you will, a universe where the last star has flickered out, where the final black hole has evaporated into quantum foam, where every possible chemical reaction has run its course and entropy has claimed its ultimate victory. This is not a place of violence or chaos. It's a realm of perfect, profound stillness, a universe at thermal equilibrium, where temperature has meaning only as a memory. In this far future cosmos, matter exists in its most fundamental state. Isolated electrons drift through space separated by distances that dwarf solar systems. The occasional positron might encounter an electron in a dance of annihilation so rare that billions of years could pass between such events. Photons, stretched by cosmic expansion into wavelengths longer than galaxies, carry the fading whispers of ancient stars. The temperature here approaches absolute zero asymptotically, forever getting closer but never quite reaching that perfect stillness where all molecular motion ceases. It's a universe in slow motion, where quantum mechanics reigns supreme, and the classical world of everyday experience has long since dissolved into statistical mechanics and probability waves. Could life exist in such a realm? The question itself stretches our definitions. Life, as we understand it, thrives on disequilibrium, on the flow of energy from hot to cold, on chemical reactions that build complexity from simplicity, on information processing that requires energy expenditure. In a universe at thermal equilibrium, there are no gradients to exploit, no energy flows to harvest. Yet some theoretical physicists have speculated about exotic forms of existence that might emerge in the deep future. Perhaps patterns of quantum fluctuations could achieve a form of organization complex enough to be called life. Maybe consciousness itself could persist as information patterns encoded in the quantum vacuum, thinking thoughts at the glacial pace of cosmic time. Freeman Dyson famously calculated that an intelligent civilization might survive the heat death by continually slowing down their thought processes, thinking each thought more slowly as the universe cools, by hibernating for exponentially longer periods between brief moments of activity. Such beings could experience an infinite subjective time, even as the universe reaches thermal equilibrium. It's a beautiful thought, consciousness as the last ember of complexity in an otherwise uniform cosmos. But these remain philosophical speculations, dreams whispered at the edge of physics. What we can say with confidence is that such a universe would be a place of extraordinary peace. No storms rage across empty space. No gravitational waves ripple through the vacuum. No electromagnetic radiation carries information from one place to another. The universe would have reached a state of perfect rest, like a cosmic meditation that continues for eternity. There's something deeply moving about this image, not tragic, but serene. The universe would have lived a full life, billions of years of star formation and galactic evolution, countless worlds where life might have emerged and flourished, civilizations that may have risen to contemplate their own existence before joining the great stillness. And at the end, not destruction, but peace, not chaos, but order, not heat, but the gentle, eternal cold of completion. In this final state, the universe becomes purely geometric, a vast space filled with the echoes of quantum uncertainty, where the only events are those allowed by the fundamental laws of physics operating at their most basic level. Time continues to flow, but it marks no changes. Space continues to expand, but it contains nothing new to separate. This vision of the far future serves as a meditation on temporality and change. It reminds us that our current universe, warm, bright, dynamic, is an extraordinary departure from equilibrium. We exist in a brief moment of cosmic flowering, when matter has organized itself into stars and planets and living beings, when energy flows from hot to cold and makes complexity possible. Our warm, breathing, thinking existence is a rare fluctuation in an otherwise still cosmos. We are witnesses to the universe's youth, participants in its grand experiment with complexity and consciousness. The cold future that awaits, if our current theories are correct, makes our present moment all the more precious. The warmth of wonder in a cold universe. As our journey through the coldest corners of the cosmos draws to a close, let's pause to reflect on the profound beauty we've discovered in realms where warmth fears to tread. We've visited places where the very concept of temperature takes on new meaning, where cold becomes not merely the absence of heat, but a pathway to understanding the deepest workings of nature. From the quantum choreography of laser-cooled atoms to the hidden oceans beneath Europa's ice, from the faithful nuclear hearts of deep space probes to the speculative slumber of cryogenic dreams, we've seen how cold can be both an obstacle to overcome and a tool for discovery. The universe's coldest places aren't barren wastelands, they're laboratories where physics reveals its most subtle secrets, and where life might find ways to flourish in conditions we never thought possible. The invisible scaffolding of dark matter shapes the cosmic web from the shadows, while our most ambitious experiments here on Earth create temperatures colder than anywhere else in the known universe. Even the theoretical heat death that awaits us in the far future carries its own strange beauty, a cosmic evening where the universe finally rests after eons of magnificent activity. These explorations remind us that our warm, dynamic cosmos is extraordinarily special. The stars that shine above us, the chemical reactions that power our cells, the very thoughts passing through our minds as we contemplate these mysteries, all of these depend on the universe being wonderfully out of thermal equilibrium. We exist in a rare moment of cosmic spring when energy flows freely and complexity blooms like flowers after a long winter. The cold reaches of space don't diminish the warmth of human curiosity and discovery. If anything, they amplify it. Each frigid moon hiding a liquid ocean, each quantum experiment approaching absolute zero, each theoretical prediction about the universe's distant future, these discoveries kindle new fires of wonder in the human imagination. As you drift off to sleep tonight, perhaps you'll dream of Europa's hidden seas stirred by Jupiter's gravitational embrace, or of atoms dancing in perfect quantum harmony in some distant laboratory, or of the Voyager probes still whispering their discoveries across the interstellar void. These are the lullabies of modern science, stories that connect us to the vast cosmos, while reminding us how precious our brief warm moment in cosmic history truly is. The universe may be vast and often cold, but it has given rise to stars and planets, to chemistry and biology, to consciousness and curiosity. In learning about the coldest places in existence, we discover not emptiness but fullness, not the absence of meaning, but its presence in forms more beautiful and strange than we ever imagined. Sweet dreams, fellow travelers. May your rest be as peaceful as the cosmic microwave background, as deep as the oceans beneath Europa's ice, and as filled with wonder as the quantum realm where atoms lose themselves in collective dreams. The universe is vast and mysterious, but tonight you are home, you are warm, and you are part of the greatest story ever told.